The Dancing Masters. An overview of the new physics. Gary Zukav. A Bantam New Age book. Bantam Books. New York, Toronto, London, Sydney, Auckland. This book is dedicated to you, who are drawn to read it. Acknowledgements. My gratitude to the following people cannot be adequately expressed. I discovered, in the course of writing this book, that physicists, from graduate students to Nobel laureates, are a gracious group of people, accessible, helpful, and engaging. This discovery shattered my long-held stereotype of the cold, objective scientific personality. For this, above all, I am grateful to the people listed here. Jack Sarfati, Ph.D., Director of the Physics/Consciousness Research Group, is the catalyst without whom the following people and I would not have met. Al-Chung Liang Huang. The Tri Chi Master, provided the perfect metaphor of Wu Li, inspiration, and the beautiful calligraphy. David Finkelstein, Ph.D., Director of the School of Physics, Georgia Institute of Technology, was my first tutor. These men are the godfathers of this book. In addition to Sarfati and Finkelstein, Brian Josephson, Professor of Physics, Cambridge University, and Max Jammer, Professor of Physics, Bar-Ilan University, Ramat Gan, Israel, read and commented upon the entire manuscript. I am especially indebted to these men, but I do not wish to imply that any one of them, or any other of the individualistic and creative thinkers who helped me with this book, would approve of it, page for page, as it is written, nor that the responsibility for any errors or misinterpretations belongs to anyone but me. I am also indebted to Henry Stapp, Ph.D., Lawrence Berkeley Laboratory, for reading and commenting upon 9x/acknowledgements portions of the manuscript, and to Elizabeth Rorscher, Ph.D., founder and sponsor of the Fundamental Physics Group, Lawrence Berkeley Laboratory, for encouraging non-physicists to partake of weekly conferences which normally would attract only physicists. In addition to Stapp and Sarfati, this group included John Clauser, Ph.D., Philippe Eberhard, Ph.D., George Weissman, Ph.D., Fred Wolf, Ph.D., and Fritjof Capra, Ph.D., among others. I am grateful to Carson Jeffries, Professor of Physics, University of California at Berkeley, for his support and for commenting upon portions of the manuscript, to David Bohm, Professor of Physics, Birkbeck College, University of London, for reading portions of the manuscript, to Saul Paul Seyrig for his frequent assistance, to the physicists of the Particle Data Group, Lawrence Berkeley Labo Ratory, for their assistance in compiling the particle table at the back of the book, to Eleanor Criswell, Professor of Psychology, Sonoma State University, California, for her valuable support, to Jin McCallum, Professor of Mathematics, Kansas State University, for her assistance and for her patient tutelage, and to Nick Herbert, Ph.D., Director of the Sea Life Institute, for providing me with his excellent papers on Bell's theorem and for permission to use his paper title, more than both as a chapter title. All of the illustrations in this book were done by Thomas Lyndon Robinson. Harvey White, Professor Emeritus, Department of PHYS. ICS, University of California at Berkeley, and former D.I. Rector, Lawrence Hall of Science, personally provided photographs of his famous simulations of probability distribution patterns. The electron diffraction photograph was provided by Ronald Grinsky, Ph.D., Lawrence Berkeley Laboratory. I learned much about spectroscopy from Sumner Davis, Professor of Physics, University of California at Berkeley. I am deeply grateful to these men who, like all of the physicists that I encountered in writing this book, acknowledgements /11, gave graciously of their time and knowledge to a stranger who needed help. I also am indebted to Maria Guarnaskelly, my editor, for her sensitivity and erudition. Without the generosity of Michael Murphy and the board of directors of the Esalen Institute, which sponsored the 1976 Conference on Physics and Consciousness, none of this probably would have happened. Table of Contents. Synoptic Table of Contents 15. Cast of Characters 19. Foreword by David Finkelstein 23. Introduction Xxei. Woolley. Big Week at Big Sur 3. Einstein doesn't like it 18. Patterns of Organic Energy. Living. 45. What Happens 67. My Way. The Role of I-91. Nonsense. Beginner's Mind 117. Special Nonsense 134. General Nonsense 160. 13. 14 /Table of Contents. 1 Clutch My Ideas. The Particle Zoo. The Dance. 191. 212. Enlightenment. More than both. The End of Science. 255. 281. Notes. Bibliography. Index. Particle Table. 315. 323. 329. 340. Synoptic Table of Contents. Woolley. Introduction. Big Week at Big Sur. Physics, 3, Esalen, 4, Chinese and English, 5, Woolley. Masters, 7, Scientists and Technicians, 9, The Sodium Spectrum, 10, Bohr's Model of the Atom, 12. Einstein doesn't like it. The New Physics and the Old Physics, 18, Newton's Physics. 21, The Great Machine, 22, Do We Create Reality? 28, The Myth of Objectivity, 30, Subatomic Particles, 31, Statistics. 33, The Kinetic Theory of Gases, 33, Probability, 35, The Copenhagen Interpretation of Quantum Mechanics, 37, Prague. Matism, 38, Split Brain Analysis, 39, Summary of the New Physics and the Old Physics, 41. Patterns of Organic Energy. Quantum Mechanics. Living. Organic and Inorganic, 45, Max Planck, 48, Discontinuous. 48, Black Body Radiation, 50, Planck's Constant, 51, Albert Einstein, 52, Einstein's Theory of the Photoelectric Effect, 53. Waves, wavelengths, frequencies, and amplitudes, 54, Diffraction, 58, Young's Double-Slit Experiment, 60, The Wave-Particle Duality, 64, probability waves, 65. What happens? The procedure of quantum mechanics, 67, the region of preparation, 68, the region of measurement, 68, the observed system, 69, the observing system, 69, the Schrödinger wave. 15. 16 / synoptic table of contents. Equation, 70, observables, 70, particles as correlations, 70. Wave functions, 73, probability functions, 73, quantum jumps. 75, the theory of measurement, 76, the metaphysics of quantum mechanics, 80, the many worlds interpretation of quantum mechanics, 83, Schrödinger's cat, 85, doubting Thomas, 88. My way, quantum mechanics. The role of one. The in here, out there illusion, 92, complementarity, 93. Compton scattering, 93, Louis de Broglie, 96, matter waves. 96, Erwin Schrödinger, 99, standing waves, 99, the Pauli exclusion principle, 103, the Schrödinger wave equation. Again, 104, Max Born, 105, probability waves, again, 106. The quantum model of the atom, 107, Werner Heisenberg. 109, the S matrix, 110, the Heisenberg uncertainty principle, 111, the tables are turned, 114. Nonsense, relativity. Beginner's mind. Nonsense, 117, the beginner's mind, 118, the special theory of relativity, L20, the Galilean relativity principle, 123, inner tile coordinate systems, 123, Galilean transformations, 125. The constancy of the speed of light, 127, the ether, 129, the Michelson-Morley experiment, 130, Fitzgerald contractions. 132, Lorentz transformations, 133. Special nonsense. The special theory of relativity, 134, proper and relative length and time, 139. Terrell's rotation explanation of relativistic contraction, 142, relativistic mass increase, 144. Simultaneity, 145, the space-time continuum, 149, the space-time interval, 150, Hermann Minkowski, 154, mass energy. 154, conservation laws, 156. General nonsense. Gravity and acceleration, 161, inside and outside the elevators, 163, gravitational mass and inertial mass, 167, the geography of the space-time continuum, 168, Euclidean geometry. Synoptic table of contents /17. 171, the revolving circles, 172, non-Euclidean geometry. 175, Einstein's ultimate vision, 179, Mercury's perihelion. 180, starlight deflection, 181, gravitational shift, 182. Black holes, 184, the illusion of force, 186, the illusion of nonsense, 187. I clutch my ideas, particle physics. The particle zoo. The barriers to change, 191, the Hall of Mirrors, 192, the New World View, 193, particle physics, 195, bubble chambers. 195, the dance of creation and annihilation, 196, what made the tracks. 198, quantum field theory, 199, the need to pretend, 201, particle masses, 202, massless particles, 205, charge, 206, spin, 207, angular momentum, 207, quantum numbers, 210, antiparticles, 210. The dance. Space-time diagrams, 212, Feynman diagrams, 214, the dance of creation and annihilation, again, 215, antiparticles, again. 217, the illusion of time, 219, entropy, 221, virtual photons. 222, the electromagnetic force, 225, Heidke-Yukawa, 226. The strong force, 226, virtual mesons, 228, self-interactions. 229, gravity, 233, the weak force, 234, virtual photons. Again, 234, vacuum diagrams, 240, conservation laws, 241. Symmetries, 243, quarks, 244, the S-matrix, again, 245. Enlightenment. Quantum logic = Bell's theorem. More than both. Physics and enlightenment, 255, Bell's theorem and quantum logic, 257, John von Neumann, 257, the description of a wave function, 257, projections as propositions, 259, the \id. Finkelstein, 261, symbols and experience, 261, logos and mythos, 261, the distributive law, 263, polarization of light. 264, the third polarizer paradox, 267, superpositions, 270. Quantum logic, 271, proof, 271, transition tables, 273. Lattices, 275, von Neumann's disproof of the distributive law. 277, quantum topology, 280. 18 / synoptic table of contents. The end of science. Enlightenment and unity, 281. J. S. Bell, 282, quantum connectedness, 282, the Einstein-Podolsky-Rosen thought experiment, 283, superluminal communication, 288, the principle of local causes, 288, Bell's theorem, 290, the Friedmann-Clauser experiment, 291, the aspect experiment, 294. Contrafactual definiteness, 299, superdeterminism, 300, the many worlds theory, again, 301, summary, 302, the philosophy Office of Quantum Mechanics, 304, David Bohm, 305, Unbro. Ken Holness, 306, Implicate Order, 307, The New Thought. Instrument, 308, Eastern Psychologies, 309, The Metaphor of Physics, 310, Kali, 311, The Path Without Form, 313, The Circle Dance, 314. Cast of Characters. Thomas Young. 1803, Double-Slit Experiment. Albert Michelson, Edward Morley. 1887, Michelson-Morley Experiment. George Francis Fitzgerald. 1892, Fitzgerald Contractions. Hendrik Antoon Lorentz. 1893, Lorentz Transformations. Electron. 1897, discovered. Max Planck. 1900, Quantum Hypothesis. Albert Einstein. 1905, Photon Theory. 1905, Special Theory of Relativity. Hermann Minkowski. 1908, Space-Time. Nucleus. 1911, discovered. Niels Bohr. 1913, Specific Orbits Model of the Atom. Albert Einstein. 1915, General Theory of Relativity. Louis de Broglie. 1924, Matter Waves. Niels Bohr, H. Kramers, John Slater. 1924, First Concept of Probability Waves. Wolfgang Pauli. 1925, Exclusion Principle. 19. XX Cast of Characters. Werner Heisenberg. 1925, Matrix Mechanics. Erwin Schrödinger. 7926, Schrödinger wave equation. 1926, equates matrix mechanics with wave mechanics. 1926, visits Bohr in Copenhagen to attack the idea of quantum jumps, and gets the flu. Max Born. 1926, probability interpretation of wave function. Niels Bohr. 1927, complementarity. Clinton Davison, Lester Germer. 1927, Davison-Germer experiment. Werner Heisenberg. 1927, uncertainty principle. Copenhagen interpretation of quantum mechanics. 1927. Paul Dirac. 1928, antimatter. Neutron. 1932, discovered. Positron. 1932, discovered. John von Neumann. 1932, quantum logic. Albert Einstein, Boris Podolsky, Nathan Rosen. 1935, EPR paper. Heidke Yukawa. 1935, predicts meson. Meson. 1947, discovered. Richard Feynman. 1949, Feynman diagrams. 16 new particles. 1947 to 1954, discovered. Many worlds interpretation of quantum mechanics. 1957. Cast of characters /XZ. David Finkelstein. 1958, One-way membrane hypothesis. Quasars. 7962, discovered. Quarks. 1964, hypothesized. J. S. Bell. 1964, Bell's theorem. David Bohm. 1970, implicate order. Henry Stapp. 1971, Non-Local Connections Re. Bell's Theorem. Stuart Friedman, John Clauser. 1972, Friedman-Clauser Experiment. 12 New Particles. 1974 to 1977, discovered. An Aspect. 1982, Aspect Experiment. Forward. When Gary Zukav announced his plans for this book, creating the outline with Al Huang and me watching at a dinner table at Salon, 1976, I did not realize the magnitude of the job he took on with such joy. Watching the book grow has been instructive and rewarding, because Zukav has insisted on going through the whole evolution of the quantum relativistic ICS of today, treating it as it is, an unfolding story. As a result, this book is not only readable, but it also puts the reader in touch with all the various ways that physicists have worked out for talking about what is so hard to talk about. In short, Gary Zukav has written a very good book for laymen. Zukav's attitude to physics is rather close to mine, so I must be a layman too, and it is more stimulating to talk ICS with him than with most professionals. He knows that physics is, among other things, an attempt to harmonize with a much greater entity than ourselves, requiring us to seek, formulate and eradicate first one and then another of our most cherished prejudices and oldest habits of thought, in a never-ending quest for the unattainable. Zukav has graciously offered me this place to add my own emphases to his narrative. Since it has been 3 years since we met, I must sift my memory for a while. Migrating whales come to mind first. I remember us standing on the Salon cliffs and watching them cavort as they headed south. Next comes to mind beautiful monarch butterflies dotting the fields from the first day, and covering one magic tree as thick as leaves in a grand finale. Between the whales and the butterflies it was difficult for us to feel self-important, and very easy for us to play. The very difficulty of communicating with the physicists at Salon helped me to realize how differently most physicists think about quantum mechanics than I do. Not that my way is 23. XXV/forward. New, it is one of two ways already pointed out in John von Neumann's 1932 book, The Mathematical Foundation of Quantum Mechanics. 1. Quantum mechanics deals with propositions defined by processes of preparation and observation involving subject and object and obeying a new logic, not with objective properties of the object alone. 2. Quantum mechanics deals with objective properties of the object alone, obeying the old logic, but they jump in a random way when an observation is made. Most working physicists seem to see one of these ways, the second, and not the other. Perhaps personality can determine the direction of science. I think there are thing minds and people minds. Good parents, psychologists and writers have to be people, while mechanics, engineers and physicists tend to be thing people. Physics has become too scary for such physicists because it is already so thingless. New evolutions, as profound as those of Einstein and Heisenberg, are waiting for a new generation of more daring and integrated thinkers. While most physicists take for granted the quantum tools of their daily work, there is a vanguard already testing roads to the next physics, and a rearguard still conscientiously holding The road back to the old Bell's theorem is mainly important to the latter, and its prominence in the book does not mean it uncovers problems in present-day quantum physics. Rather, Bell's theorem drives toward a view that most physicists already assume, that quantum mechanics is something new and different. Here it helps to distinguish between a complete theory predicting everything, what Newtonians look for. It does not seem that Newton was a strict Newtonian, since he wanted God to reset the world clock now and then, and a maximal theory, predicting as much as possible what quantum physicists look for. In spite of their controversy, Einstein and Bohr both agreed, in their different ways, that quantum mechanics is incomplete, and even that it is not vet maximal. What they really debated was whether or not an incomplete theory can be maximal. Throughout their famous controversy, Einstein argued, "Alas, our theory is too poor for experience," and Bohr replied, "No, no experience is too rich for our theory." Just as some existential philosophers despair at the indeterminacy of life and the existence of choices, and others feel ill vital. One of the features of quantum mechanics that leads to such controversy is its concern with the non-existent, the potential. There is some of this in all language, or words could only be used once, but quantum mechanics is more involved with probabilities than classical mechanics. Some people feel this discredits quantum theory, makes it less than maximal theory. So it is important to mention in defense of quantum theory that in spite of indeterminacy, quantum mechanics can be entirely expressed in yes or no terms about individual experiments, just like classical mechanics, and that probabilities can be derived as a law of large numbers and need not be postulated. I prefer to state the difference between classical and quantum theories not as presented in textbooks, but thus: once sufficient data is given, classical mechanics gives yes or no answers for all further questions, while quantum mechanics simply leaves unanswered some questions in the theory, to be answered by experience. I wish here also to note the regrettable tendency, in myself also, to feel that quantum mechanics must thereby deny physical existence to those answers that are foid in experience only, not in the theory, such as the momentum of a localized electron. So involved are we in our symbol systems. After a week of talking, the conference was still working on the elements of quantum logic, and never did get far into the new quantum time concepts we wanted to try out, but it made it easier to move on to the next set of problems, which occupy me today. Quantum mechanics is characterized by its unanswered questions. Some logicians, Martin Davis for one, have suggested these may be related to the undecidable propositions dominating logic since Gödel I used to know better. Nowadays I think they may be right. The common element being reflexivity and the impossibility for finite systems of total self-knowledge. The proper study of mankind is endless. It seems. I hope these ideas work out, and Gary Zukav writes a book about them. He does it well. David Finkelstein. New York, July 1978. Introduction. My first exposure to quantum physics occurred a few years ago when a friend invited me to an afternoon conference at the Lawrence Berkeley Laboratory in Berkeley, California. At that time, I had no connections with the scientific community. so I went to see what physicists were like. To my great surprise, I discovered that, 1. I understood everything that they said, and, 2. Their discussions sounded very much like a theological discussion. I scarcely could believe what I had discovered. Physics was not the sterile, boring discipline that I had assumed it to be. It was a rich, profound venture which had become inseparable from philosophy. Incredibly, no one but physicists seemed to be aware of this remarkable development. As my interest in and knowledge of physics grew, I resolved to share this discovery with others. This book is a gift of my discovery. It is one of a series. Generally speaking, people can be grouped into two categories of intellectual preference. The first group prefers explorations which require a precision of logical processes. These are the people who become interested in the natural sciences and mathematics. They do not become scientists because of their education, they choose a scientific education because it gratifies their scientific mental set. The second group prefers explorations which involve the intellect in a less logically rigorous manner. These are the people who become interested in the liberal arts. They do not have a liberal arts mentality because of their education, they choose a liberal arts education because it gratifies their liberal arts mental set. Since both groups are intelligent, it is not difficult for members of one group to understand what members of the other group are studying. However, I have discovered a no-table communication problem between the two groups. Many times my physicist friends have attempted to explain a introduction concept to me and, in their exasperation, have tried one explanation after another, each one of which sounded, to me, abstract, difficult to grasp, and generally abstruse when I could comprehend, at last, what they were trying to communicate. Inevitably I was surprised to discover that the idea itself was actually quite simple. Conversely, I often have tried to explain a concept in terms which seemed, to me, laudably lucid, but which, to my exasperation, seemed hopelessly vague, ambiguous, and lacking in precision to my physicist friends. I hope that this book will be a useful translation which will help those people who do not have a scientific mental set, like me, to understand the extraordinary process which is occurring in theoretical physics. Like any translation, it is not as good as the original work and, of course, it is subject to the shortcomings of the translator. For better or worse, my first qualification as a translator is that, like you, I am not a physicist. To compensate for my lack of education in physics, and for my liberal arts mentality, I asked, and received, the assistance of an extraordinary group of physicists. They are listed in the acknowledgements, 4 of them in particular. Read the entire manuscript. As each chapter was completed, I sent a copy of it to each physicist and asked him to correct any conceptual or factual errors which he found. Several other physicists read selected chapters. My original intention was to use these comments to correct the text. However, I soon discovered that my physicist friends had given more attention to the manuscript than I had dared to hope. Not only were their comments thoughtful and penetrating, but, taken together, they formed a significant volume. of information by themselves. The more I studied them, the more strongly I felt that I should share these comments with you. Therefore, in addition to correcting the manuscript with them, I also included in the footnotes those comments which do not duplicate the corrected text. In particular, I footnoted those comments which would have slowed the flow of the text or made it technical, and those comments which disagreed with the text and also disagreed with the comments of the other physicists. By publishing dissenting opinions in the footnotes, I have been able to include numerous ideas which would have lengthened and complicated the book if they had been presented in the text from the beginning of the dancingmasters to the end. No term is used which is not explained immediately before or after its first use. This rule is introduction/6 not followed in the footnotes. This gives the footnotes an unmitigated freedom of expression. However, it also means that the footnotes contain terms that are not explained before, during, or after their use. The text respects your status as newcomer to a vast and exciting realm. The footnotes do not. However, if you read the footnotes as you read the book, you will have the rare opportunity to see what four of the finest physicists in the world have to say about it as they in effect read it along with you. Their footnotes punctuate, illustrate, annotate, and jab at everything in the text better than it can be described. These footnotes reveal the aggressive precision with which men of science seek to remove the flaws from the work of a fellow scientist, even if he is an untrained colleague, like me, and the work is non-technical, like this book. The new physics, as it is used in this book, means quantum mechanics, which began with Max Planck's theory of quanta in 1900, and relativity, which began with Albert Einstein's special theory of relativity in 1905. The old physics is the physics of Isaac Newton, which he discovered about 300 years ago. Classical physics means any physics that attempts to explain reality in such a manner that for every element of physical reality there is a corresponding element in the theory. Therefore, classical physics includes the phys. ICS of Isaac Newton and relativity, both of which are structured in this one-to-one manner. It does not, however, include quantum mechanics, which, as we shall see, is one of the things that makes quantum mechanics unique. Be gentle with yourself as you read. This book contains many rich and multifaceted stories, all of which are heady pun stuff. You cannot learn them all at once any more than you can learn the stories told in War and Peace, Crime and Punishment, and Les Miserables all at once. I suggest that you read this book for your pleasure, and not to learn what is in it. There is a complete index at the back of the book and a good table of contents in the front. Between the two of them, you can return to any subject that catches your interest more. Over by enjoying yourself, you probably will remember more than if you had set about to learn it all. One last note: this is not a book about physics and Eastern philosophies, although the poetic framework of Woolley is conducive to such comparisons. This book is about quantum phys. ICS and relativity. In the future I hope to write another book, XXX/introduction, specifically about physics and Buddhism, in view of the Eastern flavor of Woolley. However, I have included in this book those similarities between Eastern philosophies and physics that seemed to me so obvious and significant that I felt that I would be doing you a disservice if I did not mention them in passing. Happy reading. Gary Zukav. San Francisco, July 1978. Most of the fundamental ideas of science are essentially simple, and may, as a rule, be expressed in a language comprehensible to everyone. Albert Einstein. Even for the physicist, the description in plain language will be a criterion of the degree of understanding that has been reached. Werner Heisenberg too. If you cannot, in the long run, tell everyone what you have been doing, your doing has been worthless. Erwin Schrödinger 3. The Dancing Masters. Part 1. Woolley. Chapter 1. Big Week at Big Sur. When I tell my friends that I study physics, they move their heads from side to side, they shake their hands at the wrist, and they whistle, phew. That's difficult. This universal reaction to the word physics is a wall that stands between what physicists do and what most people think they do. There is usually a big difference between the two. Physicists themselves are partly to blame for this sad situation. Their shop talk sounds like advanced Greek, unless you are Greek or a physicist. When they are not talking to other physicists speak English. Ask them what they do. However, and they sound like the natives of Corfu again. On the other hand, part of the blame is ours. Generally speaking, we have given up trying to understand what physicists and biologists, etc., really do. In this we do ourselves a disservice. These people are engaged in extremely interesting adventures that are not that difficult to understand. True. How they do what they do sometimes entails a technical explanation which, if you are not an expert, can produce an involuntary deep sleep. What physicists do, however, is actually quite simple. They wonder what the universe is really made of, how it works, what we are doing in it, and where it is going, if it is going any place at all. In short, they do the same things that we do on starry nights when we look up at the vastness of the universe and feel overwhelmed by it and a part of it at the same time. That is what physicists really do. And the clever rascals get paid for doing it. Unfortunately, when most people think of physics, they think of chalkboards covered with undecipherable symbols of 4/Woolley, an unknown mathematics. The fact is that physics is not math. Ematics. Physics, in essence, is simple wonder at the way things are and a divine, some call it compulsive, interest in how that is so. Mathematics is the tool of physics. Stripped of mathematics, physics becomes pure enchantment. I had spoken often to Jack Sarfati, who is the physicist director of the Physics/Consciousness Research Group, about the possibility of writing a book, unencumbered with technicalities and mathematics, to explain the exciting insights that motivate current physics. So when he invited me to a conference on physics that he and Michael Murphy were arranging at the Esalen Institute, I accepted with a purpose. The Esalen Institute, it is named for an Indian tribe, is in Northern California. The Northern California coast is an some combination of power and beauty, but nowhere so much as along the Pacific Coast Highway between the towns of Big Sur and San Luis Obispo. The Esalen facilities are located about a half-hour south of Big Sur between the highway and the coastal mountains on the one side and rugged cliffs overlooking the Pacific Ocean on the other. A dancing stream divides the northern third of the grounds from the remainder. On that side is a big house, called the Big House, where guests stay and groups meet, along with a small home where Dick Price, co-founder of eSalon with Murphy, stays with his family. On the other side of the stream is a lodge where meals are served and meetings are held, accommodations for guests and staff, and hot sulfur baths. Dinner at eSalon is a multidimensional experience. The elements are candlelight, organic food, and a contagious naturalness that is the essence of the eSalon experience. Sarfati and I joined two men who already were eating. One was David Finkelstein, a physicist from Yeshiva University, in New York, who was attending the conference on physics. The other was Al Chungliang Huang, a Trek master who was leading a workshop at eSalon. We could not have chosen better companions. The conversation soon turned to physics. When I studied physics in Taiwan, said Huang, we called it Wuli, pronounced Wuli. It means patterns of organic energy. Everyone at the table was taken at once by this image. Mental lights flashed on, one by one, as the idea penetrated. Big week at Big Sur /5. Wuli was more than poetic. It was the best definition of physics that the conference would produce. It caught that certain something, that living quality that we were seeking to express in a book, that thing without which physics becomes sterile. Let's write a book about Wuli. I heard myself exclaim. Immediately, ideas and energy began to flow, and in one stroke all of the prior planning that I had done went out the window. From that pooling of energy came the image of the dancing Wuli masters. My remaining days at eSalon and those that followed were devoted to finding out what Wuli masters are, and why they dance. All of us sensed with excitement and certitude that we had discovered the channel through which the very things that we wanted to say about physics would flow. The Chinese language does not use an alphabet like Western languages. Each word in Chinese is depicted by a character, which is a line drawing. Sometimes two or more characters are combined to form different meanings. This is why it is difficult to translate Chinese into English. Good translations require a translator who is both a poet and a linguist. For example, Wu can mean either matter or energy. Li is a richly poetic word. It means universal order or universal law. It also means organic patterns. The grain in a panel of wood is Li. The organic pattern on the surface of a leaf is also Li, and so is the texture of a rose petal. In short, Wuli, the Chinese word for physics, means turns of organic energy, matter / energy, Wu, plus universal order / organic patterns, Li. This is remarkable since it reflects a world view which the founders of Western science, Galileo and Newton, simply did not comprehend, but toward which virtually every physical theory of import in the 20th century is pointing. The question is not, do they know some thing that we don't? The question is, how do they know it? English words can be pronounced almost any way without changing their meanings. I was 5 years a college graduate before I learned to pronounce consummate as an adjective. Consummate. It means carried to the utmost extent or degree, perfect. I live in anguish when I think of the times that I have spoken of consummate linguists, consummate scholars, etc. Someone always seemed to be holding back a 6/woolly smile. Almost I learned later that these were the people who read dictionaries nonetheless. My bad pronunciation never prevented me from being understood. That is because inflections do not change the denotation of an English word no. Spoken with a rising inflection, no, with a downward inflection, no, and with no inflection, no, all mean. According to the dictionary, a denial, a refusal, negative. This is not so in Chinese. Vlost Chinese syllables can be pronounced several different ways. Each different pronunciation is a different word which is written differently and which has a meaning of its own. Therefore, the same syllable pronounced with different inflections, which unaccustomed Western listeners scarcely can distinguish, constitutes distinctly separate words, each with its own ideogram and meaning, to a Chinese listener in English, which is an atonal language. These different ideograms are all written and pronounced the same way. For example, there are over 80 different WS in Chinese, J, of which are spelled and pronounced the same way. In English, Huang has taken 5 of these WS, each of which, when combined with Li, produces a different Wu. Li, each with the same English spelling, and each pronounced in English, Wu Li. The first Wu Li means patterns of organic energy. This is the Chinese way of saying pH. 6, Wu means matter or energy. The second Wu Li means my way, Wu Inian's mine or self. The third Wu Li means nonsense, Wu means void or non-bemg. The fourth Wu Li means I clutch my ideas, Wu means to make a fist or clutch with a closed hand. The fifth Wu Li means enlightenment, Wu Inian's enlightenment or my heart /MV mind. If we were to stand behind a master weaver as he begins to work his loom, we would see, at first, not cloth, but a multitude of brightly colored threads from which he picks and chooses with his expert eye, and feeds into the moving shuttle. As we continue to watch, the threads blend one into the other, a fabric appears, and on the fabric, behold, a pattern emerges. In a similar manner, Huang has created a beautiful tapestry from his own epistemological loom. Big week at Big Sur /7. Physics equals Wu Li. Wu Li equals patterns of organic energy. Wu Li equals my way. Wu Li equals nonsense. Wu Li equals I clutch MV ideas. Wu Li equals enlightenment. Each of the physicists at the conference, to a person, reported resonance with this rich metaphor. Here, at last, was the vehicle through which we could present the seminal elements of advanced physics. By the end of the week, everyone at Salon was talking about Wu Li. At the same time TBA this was happening, I was TRMG2. If in doubt what a master is, the dictionary was no help. All of its definitions involved an element of control. This did not fit easily into our image of the dancing Wu Li masters. Since Al Luang is a Tri master, I asked him. That is the word that other people use to describe me. He aid to Huang. Huang was just Huang. Later in the week, I asked him the same question again. hoping to get a more tangible answer. A master is someone who started before you did was what I got that time. MV Western education left me unable to accept a non-defim. I on for my definition of a master, so I began to read Huang's Cock, Embrace Tiger, Return to Mountain there, in the Breward by Alan Watts, in a paragraph describing L. Huang. Found what I sought, said Alan Watts of L. Huang. He begins from the center and not from the fringe. He imparts an understanding of the basic principles of the art before going on to the meticulous details. And he refuses to break down the Tri movements into a 1-2-3 drill so as to make the student into a robot. The traditional way is to teach by rote, and to give the impression that long periods of boredom are the most essential part of training. In that way a student may go on for years and years without ever getting the feel of what he is doing. Here was just the definition of a master that I sought. A faster teaches essence when the essence is perceived. He caches what is necessary to expand the perception. The Wu 8/Wu Li. Li master does not speak of gravity until the student stands in wonder at the flower petal falling to the ground. He does not speak of laws until the student, of his own, saves. How strange! I drop 2 stones simultaneously, one heavy and one light. And both of them reach the earth at the same moment. He does not speak of mathematics until the student saves. There must be a way to express this more simply. In this way, the Wu Li master dances with his student. The Wu Li master does not teach, but the student learns. The Wu Li master always begins at the center, at the heart of the matter. This is the approach that we take in this book. It is written for intelligent people who want to know about advanced physics but who are ignorant of its terminology and perhaps of its mathematics. The Dancing Wu Li Masters is a book of essence, the essence of quantum mechanics, quantum logic, special relativity, general relativity, and some new ideas that indicate the direction that physics seems to be moving. Of course, who can know where the future goes? The only surety is that what we think today will be a part of the past tomorrow. Therefore, this book deals not with knowledge, which is always past tense anyway, but with imagination, which is physics come alive, which is Wu Li. One of the greatest physicists of all, Albert Einstein, was perhaps a Wu Li master. In 1938 he wired, "Physical concepts are free creations of the human mind, and are not, however it may seem, uniquely determined by the external world. In our endeavor to understand reality we are somewhat like a man trying to understand the mechanism of a closed watch. He sees the face and the moving hands, even hears its ticking, but he has no way of opening the case. If he is ingenious he may form some picture of a mechanism which could be responsible for all the things he observes. But he may never be quite sure his picture is the only one which could explain his observations. He will never be able to compare his picture with the real mechanism, and he cannot even imagine in the possibility of the meaning of such a comparison. Too, most people believe that physicists are explaining the world. Some physicists even believe that, but the Wu Li masters know that they are only dancing with it. I asked Huang how he structures his classes. Big week at Big Sur /9. Every lesson is the first lesson, he told me every time we dance, we do it for the first time. But surely you cannot be starting new each lesson, I said. Lesson number 2 must be built on what you taught in lesson number 1, and lesson 3 likewise must be built on lessons 1 and 2, and so on. When I say that every lesson is the first lesson, he replied, it does not mean that we forget what we read. No, it means that what we are doing is always new because we are always doing it for the first time. This is another characteristic of a master. Whatever he does with the enthusiasm of doing it for the first time. This is the source of his unlimited energy. Every lesson that he teaches, or learns, is a first lesson. Every dance that he dances for the first time. It is always new, personal, and alive. Isidore Irabi, Nobel Prize winner in physics and the former chairman of the physics department at Columbia University, wrote, "We don't teach our students enough of the intellectual content of experiments, their novelty and their capacity for opening new fields. My own view is that you take these things personally. You do an experiment because your own philosophy makes thou want to know the result. It's too hard and life is too short to spend your time doing something because someone else has said it's important. You must feel the thing yourself." 3. Unfortunately, most physicists are not like Rabbi. The majority of them, in fact, do spend their lives doing what other people have told them is important. That was the point Rabbi was making. This brings us to a common misunderstanding. When most people say scientist, they mean technician. A technician is a highly trained person whose job is to apply known techniques and principles. He deals with the known. A scientist is a person who seeks to know the true nature of physical reality. He deals with the unknown. In short, scientists discover and technicians apply. However, it is no longer evident whether scientists really discover new things or whether they create them. And people believe that discovery is actually an act of creation. If this is then the distinction between scientists, poets, painters, 10/WLP, and writers is not clear. In fact, it is possible that scientists, poets, painters and writers are all members of the same family of people whose gift it is by nature to take those things which we call commonplace and to represent them to us in such ways that our self-imposed limitations are expanded. Those people in whom this gift is especially pronounced, we call geniuses. The fact is that most scientists are technicians. They are not interested in the essentially new. Their field of vision is relatively narrow. Their energies are directed toward applying what is already known because their noses often are buried in the bark of a particular tree. It is difficult to speak meaningfully to them of forests. The case of the mysterious hydrogen spectrum illustrates the difference between scientists and technicians. When a white light, such as sunlight, enters a glass prism, one of the most beautiful of phenomena occurs. Out the other side of the PNSM comes not white light, but every color in the rainbow, from dark red to light violet, with orange, yellow, green and blue in between. This is because white light is made of all these different colors. It is a combination, whereas red light contains only red light, green light contains only green light, etc. Isaac Newton wrote his famous Optics about this phenomenon 300 years ago. This display of colors is called a white light spectrum. The spectral analysis of white light shows a complete spectrum because white light contains all of the colors that our eyes can see, and some that they cannot see, like infrared and ultraviolet. However, not every spectral analysis produces a complete spectrum if we take one of the chemical elements, for example, like sodium, cause it to emit light, and shine that light through a glass prism. We get only part of a complete spectrum. If an object is visible in a dark room, it is emitting light. If it appears red, for example, it is emitting red light. Light is emitted BV. Excited objects exciting a piece of sodium does not mean offering it tickets to the Super Bowl. Exciting a piece of sodium means adding some energy to it. One way of doing this is to heat it when we shine the light emitted by excited, incandescent, sodium through a PNSM, or spectroscope. We do not obtain the full array of colors characteristic of white light, but only parts of it. In the case of sodium, we obtain two thin yellow lines. Big weak at Big Sur /11. We also can produce a negative image of the sodium spectrum by shining white light through sodium vapor to see what parts of the white light the sodium vapor absorbs. White light passing through sodium vapor and then through a spectroscope produces the whole rainbow of colors minus the two yellow lines emitted BV incandescent sodium. Either way, the sodium spectrum always produces the same distinct pattern. It may be composed of black lines on an otherwise complete spectrum of colors, or it may be composed of colored lines without the rest of the spectrum, but it always remains the same. This pattern is the fingerprint of the element sodium. Each element emits, or absorbs, on specific colors. Likewise, each element produces a specific spectroscopic pattern which never varies. Hydrogen is the simplest element. It seems to have only two components, a proton, which has a positive charge, and an electron, which has a negative charge. We must say it seems to have because there is not one person alive who has ever seen a hydrogen atom. If hydrogen atoms exist, millions of them can exist on a pinhead, so small are they. Calculated to be hydrogen atoms is a speculation about what is inside of the watch. We can say only that the existence of such entities nicely explains certain observations that would be very difficult to explain otherwise, barring explanations such as the devil did it, which still may prove to be correct. It is this kind of explanation that drove Galileo, Newton, and Descartes to create what is now modern science. At one time, physicists thought that atoms were constructed in the following way. At the center of an atom is a nucleus. Just as the Sun is at the center of our solar system, in the nucleus is located almost all of the mass of the atom in the form of positively charged particles, protons, and particles about the same size as protons but without a charge, neutrons. Only hydrogen has no neutrons in its nucleus. Orbiting about the nucleus, as the planets orbit the Sun, are electrons, which have almost no mass compared with the nucleus. Each electron has one negative charge. The number of electrons is always the same as the number of protons, so that the positive and negative charges cancel each other, and the atom, as a whole, has no charge. In practice, some of the lines represent transitions between higher energy states do not appear in absorption spectra. 12/Woolley. The problem with comparing this model of the atom with our solar system is that the distances between an atomic nucleus and its electrons are enormously greater than we picture the distances between the Sun and its planets. The space occupied by an atom is so huge, compared with the mass of its particles, almost all of which is in the nucleus, that the electrons orbiting the nucleus are like a few flies in a cathedral AC. According to Ernest Rutherford, who created this model of the atom in 1911. This is the familiar picture of the atom that most of us learned in school, usually under duress. Unfortunately, this picture is obsolete, so you can forget the whole thing. We will discuss later how physicists currently think of an atom. The point here is that the planetary model of the atom formed the background against which a most puzzling problem was solved. The spectrum of hydrogen, the simplest of the atoms, contains over 100 lines. The patterns of the other elements are even more complicated. When we shine the light from excited hydrogen gas through a spectroscope, we get over 100 different lines of color in a distinct pattern. The question is, how can such a simple thing like a hydrogen atom, which has only two components, a proton and an electron, account for such a complex spectrum? One way of thinking about light is to ascribe wave-like properties to it, and then to say that different colors have different frequencies, just as different sounds, which also are waves, have different frequencies. Arnold Sommerfeld, a German physicist who also was an accomplished pianist, observed, tongue-in-cheek, that hydrogen atoms, which emit over 100 different frequencies, must be more complicated than grand pianos, which emit only 88 different frequencies. It was a Danish physicist named Niels Bohr who came up with an explanation, in 1913, that made so much sense that it won him a Nobel Prize. Like most ideas in physics, it is essentially simple. Bohr did not start with what was theoretically accurately speaking, different experimental equipment is required to photograph each series of the hydrogen spectrum. Therefore, most single photographs of the hydrogen spectrum show only about 10 lines. Theoretically, there are an infinite number of lines in each atomic spectrum. In feet, theoretically, there are an infinite number of lines in each series of each spectrum, because the lines in that higher frequency range of each series become so closely spaced that effect they form continuum. Big week at Big Sur /13. Known about the structure of atoms. He started with what he really knew about atoms, that is, he started with raw spectroscopic data. Bohr speculated that electrons revolve around the nucleus of an atom not at just any distance, but in orbits or shells, which are specific distances from the nucleus. Each of these shells, theoretically there are an infinite number of them, contains up to a certain number of electrons, but no more. If the atom has more electrons than the first shell can accommodate, the electrons begin to fill up the second shell. If the atom has more electrons than the first and second shells combined can hold, the third shell begins to fill, and so on. Like this. Shell number 1 2 3 4 5. Numbers of electrons 2 8 18 32 50. His calculations were based on the hydrogen atom, which has only one electron. According to Bohr's theory, the electron in the hydrogen atom stays as close to the nucleus as it can get. In other words, it usually is in the first shell. This is the lowest energy state of a hydrogen atom. Physicists call the lowest energy state of any atom its ground state. If we excite an atom of hydrogen, we cause its electron to jump to one of the outer shells. How far it jumps depends upon how much energy we give it. If we really heat the atom up, thermal Energy, we cause its electron to make a very large jump all the way to one of the outer shell's smaller amounts of energy. Make the electron jump less far, however, as soon as it can. When we stop heating it, the electron returns to a shell closer in. Eventually it returns all the way back to shell number 1 whenever the electron jumps from an outer shell to an inner shell. It emits energy in the form of light. The energy that the electron emits is exactly the amount of energy that it absorbed when it jumped outward in the first place. Bohr discovered that all of the possible combinations of jumps that the hydrogen electron can make on its journeys back to the ground state, the first shell, equals the number of lines in the hydrogen spectrum. This is Bohr's famous solution to the grand piano mystery. If the electron in a hydrogen atom travels from an outer shell all the way to the innermost shell in one jump, it gi/s off a certain amount of energy that makes one line in the hydro 14/Woolley gen spectrum. If the electron in a hydrogen atom makes a tiny jump from an outer shell to the next shell inward, it gives off a much smaller amount of energy that makes another spectral line. If the electron in a hydrogen atom jumps from shell 5 to shell 3, for example, that makes yet another line. A jump from shell 6 to shell 4 and then from shell 4 to shell 1 makes 2 more spectral lines, and so on. In this way we can account for the entire hydrogen spectrum. If we excite a hydrogen atom with white light instead of heat, we can produce the absorption phenomenon that we mentioned earlier. Each electron jump from an inner shell to a shell farther out requires a certain amount of energy, no more and no less. An electron jump from shell 1 to shell 2 requires a certain amount of energy, and only that amount. The same is true for a jump from shell 5 to shell 7, etc. Each jump that the electron makes from an inner shell to an outer shell takes a specific amount of energy. No more and no less. When we shine white light on a hydrogen atom, we are offering it a whole supermarket of different energy amounts. However, it cannot use all that we have to offer, only certain specific amounts. If its electron jumps from shell 1 to shell 4, for example, it takes that particular energy package out of the array of energy packets that we are giving it. The package that it takes out becomes a black line in the otherwise complete spectrum of white light. A jump from shell 3 to shell 4 becomes another black line. A jump from shell 1 to shell 2, and then from shell 2 to shell 6, there are all sorts of combinations, makes 2 more black lines. In sum, if we shine white light through hydrogen gas and then through a prism, the result is the familiar white light spectrum, but with over 100 black lines in it. Each of these black lines corresponds to a specific energy amount that was required to make a hydrogen electron jump from one shell to another shell farther out. These black lines in the white light spectrum form exactly the same pattern that we get when we shine the light emitted from excited hydrogen gas directly through a prism, except in that case, the lines are colored and the rest of the white light spectrum is missing. Of course, the colored lines are caused by the electrons returning to lower level shells and, in the process, emitting energy amounts equal to what they absorbed when we first made them. Bohr's theory or Vernet. Big week at Big Sur /15. TED physicists to calculate the frequencies of the light given off by simple hydrogen atoms. These calculations agreed with observations. The grand piano mystery was solved. Shortly after Bohr published his theory in 1913, an army of physicists began the work of applying it to the other elements. This process was quite complicated for atoms with large numbers of electrons, and not all of the questions that physicists had about the nature of atomic phenomena were answered. Nonetheless, a tremendous amount of knowledge was gained. From this work, most of the physicists who went to work on Bohr's theory, applying it and further developing it, were technicians. Bohr himself, one of the founders of the new physics, was a scientist. This is not to say that technicians are not important. The technician and the scientist form a partnership. Bohr could not have formulated his theory without the wealth of spectroscopic data at his disposal. That data was the result of countless laboratory hours. It was beyond Bohr's capacity, as one person, to substantiate his theory. Technicians did this for him. BV applying it to the other elements. Technicians are important members of the scientific community. However, since this is a book about Woolly masters and not about technicians, we will use the word physicist from now on to mean those physicists who are also scientists, that is, those physicists, people, who are not confined. BV the known. From the little that we know about Woolly masters, it is evident that they come from this group. There are certain limitations which no book on physics can overcome. First, there is so much to present that not even 20 volumes could contain it all. There is that much new material published each year. Even physicists find it impossible to keep abreast of the whole field. It requires a steady diet of reading just to keep current in one area. For everything that is included in these pages, there is much more that is not. No matter how much thou learn about physics, there always will be something that is new to thou. Physicists have this problem, too. Second, no complete appreciation of physics is possible without mathematics. Nonetheless, there is no mathematics in the Dancing Woolly Masters. Mathematics is a highly structured way of thinking. Physicists view the world in this way. One point of view is that they impose this structure on 16/Woolly, what they see. Another point of view is that the world presents itself most completely through such structures. In any case, mathematics is the most concise expression of physics. The reason for writing the Dancing Woolly Masters, however, is that most physicists are not able to explain physics very well without it. This makes them very concise but, unfortunately, unintelligible. The fact is that most of us use words to do our explaining. However, it is important to remember that mathematics and English are both languages. Languages are useful tools for conveying information, but if we try to communicate experiences with them, they simply do not work. All a language can do is talk about an experience. Woolly masters know that a description of an experience is not the experience. It is only talk about it. This is a book about physics. Therefore, all it contains is a description. It cannot contain the experience itself. This does not mean that you will not have the experience of physics by reading it. It only means that if you do, the experience is coming from you, and not from the book. Quantum mechanics, ICS, for example, shows us that we are not as separate from the rest of the world as we once thought. Particle physics shows us that the rest of the world does not sit idly out there. It is a sparkling realm of continual creation, transformation, and annihilation. The ideas of the new physics, when wholly grasped, can produce extraordinary experiences. The study of relativity theory, for example, can produce the remarkable experience that space and time are only mental constructions. Each of these different experiences is capable of changing us in such ways that we never again are able to view the world as we did before. There is no single experience of physics. The experience always is changing. Relativity and quantum mechanics, although generally unknown to non-physicists, are more than a half-century old. Today, the entire field of physics is quivering with anticipation. The air is charged with excitement. A feeling is shared among physicists that radical change is at hand. A consensus grows that the near future will see new theories exploding onto the scene, incorporating the older theories, and giving us a much larger view of our universe and, consequently, of ourselves. The Woolly Masters move in the midst of all this, now dancing this way, now that, sometimes with a heavy beat. Big week at Big Sur /17. Sometimes with a lightness and grace, ever flowing freely. Now they become the dance, now the dance becomes them. This is the message of the Woolly Masters, not to confuse the type of dance that they are doing with the fact that they are dancing. Chapter 1. Einstein doesn't like it. Quantum mechanics are not the fellows who repair automobiles in Mr. Quantum's garage. Quantum mechanics is a branch of physics. There are several branches of physics. Most physicists believe that sooner or later they will construct an overview large enough to incorporate them all. According to this point of view, we eventually will develop, in principle, a theory which is capable of explaining everything so well that there will be nothing left to explain. This does not mean, of course, that our explanation necessarily will reflect the way that things actually are. We still will not be able to open the watch, as Einstein put it, but every occurrence in the real world, inside the watch, will be accounted for by a corresponding element of our final super theory. We will have, at last, a theory that is consistent within itself and which explains all observable phenomena. Einstein called this state the ideal limit of knowledge. This way of thinking runs into quantum mechanics the same way that the car runs into the proverbial brick wall. Einstein spent a large portion of his career arguing against quantum mechanics, even though he himself made major contributions to its development. Why did he do this? To ask this question is to stand at the edge of an abyss, still on the solid ground of Newtonian physics, but looking into the void. To answer it is to leap boldly into the new physics. Quantum mechanics forced itself upon the scene at the beginning of this century. No convention of physicists voted. 18. Einstein doesn't like it/19. To start a new branch of physics called quantum mechanics. No one had any choice in the matter, except, perhaps, what to call it. A quantum is a quantity of something, a specific amount. Mechanics is the study of motion. Therefore, quantum Mechanics is the study of the motion of quantities. Quantum theory says that nature comes in bits and pieces, quanta, and quantum mechanics is the study of this phenomenon. Quantum mechanics does not replace Newtonian physics, it includes it. The physics of Newton remains valid within its limits. To say that we have made a major new discovery about nature is one side of a coin. The other side of the coin is to say that we have found the limits of our previous theories. What we actually discover is that the way that we have been looking at nature is no longer comprehensive enough to explain all that we can observe, and we are forced to develop a more inclusive view. In Einstein's words, creating a new theory is not like destroying an old barn and erecting a skyscraper in its place. It is rather like climbing a mountain, gaining new and wider views, discovering unexpected connections between our starting point and its rich environment. But the point from which we started out still exists and can be seen, although it appears smaller and forms a tiny part of our broad view, gained by the mastery of the obstacles on our adventurous way up. Newtonian physics still is applicable to the large-scale world, but it does not work in the subatomic realm. Quantum mechanics resulted from the study of the subatomic realm, that invisible universe underlying, embedded in, and forming the fabric of everything around us. In Newton's age, late 1600s, this realm was entirely speculation. The idea that the atom is the indivisible building block of nature was proposed about 400 years before Christ, but until the late 1800s it remained just an idea. Then, physicists developed the technology to observe the effects of atomic phenomena, thereby proving that atoms exist. Of course, what they really proved was that the theoretical existence of atoms was the best explanation of the experimental data that anyone could invent at the time. They also proved that atoms are not indivisible, but themselves are made of 20⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ protons, and neutrons. These new particles were labeled elementary particles because physicists believed that, at last, they really had discovered the ultimate building blocks of the universe. The elementary particle theory is a recent version of an old Greek idea to understand the theory of elementary particles. Imagine a large city made entirely of bricks. This city is filled with buildings of all shapes and sizes, every one of them, and the streets as well, have been constructed with only a few different types of brick. If we substitute universe for city and particle for brick, we have the theory of elementary particles. It was the study of elementary particles that brought physicists nose to nose with the most devastating, to a physicist, discovery. Newtonian physics does not work in the realm of the very small asterisk. The impact of that earth-shaking discovery still is reshaping our worldview. Quantum mechanical experiments repeatedly produced results which the physics of Newton could neither predict nor explain yet, although Newton's physics could not account for phenomena in the microscopic realm. It continued to explain macroscopic phenomena very well, even though the macroscopic is made of the microscopic. This was perhaps the most profound discovery of science. Newton's laws are based upon observations of the everyday world they predict events. These events pay on to real things. Like baseballs and bicycles, quantum mechanics is based upon experiments conducted in the subatomic realm. It predicts probabilities. These probabilities pertain to subatomic phenomena. Subatomic phenomena cannot be observed directly. None of our senses can detect them. Not only has no one ever seen an atom, much less an electron, no one has ever tasted, touched, heard, or smelled one either. Newton's laws depict events which are simple to understand and easy to picture. Quantum mechanics depicts the probabilities of phenomena which defy conceptualization and are impossible to visualize. Therefore, these phenomena must be understood in a way that is not more difficult than our usual way of understanding, but different from it. Do not try to make a complete mental picture of quantum mechanical events. The Deke-adapted Eve can detect a single photon, otherwise on the effect of subatomic phenomena are available to our senses, a track on a photographic plate, a pointer movement on a meteor, etc. Einstein doesn't like it/21. Physicists make partial pictures of quantum phenomena, but even these pictures have a questionable value. Instead, allow yourself to be open without making an effort to visualize anything. Werner Heisenberg, one of the founders of quantum physics, wrote, "The mathematically formulated laws of quantum theory show clearly that our ordinary intuitive concepts cannot be unambiguously applied to the smallest particles. All the words or concepts we use to describe ordinary physical objects, such as position, velocity, color, size, and so on, become indefinite and problematic if we try to use them of elementary particles. 3. The idea that we do not understand something until we have a picture of it in our heads is a byproduct of the Newtonian way of looking at the world. If we want to get past Newton, we have to get past that. Newton's first great contribution to science was the laws of motion. If an object, said Newton, is moving in a straight line, it will continue moving in a straight line forever unless it is acted upon by something else, a force. At that time its direction and speed will be altered, depending upon the magnitude and direction of the force which it encounters. Furthermore, every action is accompanied by an equal and opposite reaction. Today, these concepts are familiar to anyone who has studied physics or hung out in a pool hall. However, if we mentally project ourselves 300 years into the past, we can see how remarkable they really are. First, Newton's first law of motion defied the accepted authority of the day, which was Aristotle. According to Aristotle, the natural inclination for a moving object is to return to a state of rest. Second, Newton's laws of motion describe events which were unobservable in the 1600s in the everyday world, which was all that Newton had to observe. Moving objects always do return to a state of rest because of friction. If we put a wagon in motion, it encounters friction from the air through which it passes, from the ground its tires move on, from the axles that its wheels turn around, and, unless it is rolling downhill, sooner or later it comes to rest. We can streamline the wagon 22/Woolley. Grease the whittles and use a smooth road, but this only reduces the effect of friction. Eventually the wagon stops moving, apparently on its own. Newton never had the chance to see a film of astronauts in space, but he predicted what THEV would encounter when an Astronaut releases a pencil in front of him, nothing happens, it just stays there. If he gives it a push, off it goes in the direction of the push until it bumps into a wall. If the wall were not there, the pencil would continue to move uniformly in principle, forever. The astronaut also moves off in the opposite direction, but much more slowly because of his greater mass. Third, Newton's premise was I make no hypotheses, HV. Hypothesis non fingo, which means that he based his laws upon sound experimental evidence and nothing else. His criteria for the validity of everything that he wrote was that anyone should be able to reproduce his experiments and come up with the same results if it could be verified experimentally. It was true. If it could not be verified experimentally, it was suspect. The Church took a dim view to save the least of this position, since it had been saving things for 1500 years which hardly were subject to experimental verification. Newtonian physics, in effect, was a direct challenge to the power of the Church. The power of the Church was considerable. Shortly before Newton's birth, Galileo was seized by the Inquisition for declaring that the earth revolves around the sun and for drawing unacceptable theological implications from his beliefs. He was forced to recant on penalty of imprisonment or worse. This made a considerable impression on people, among them another founder of modern science, the Frenchman René Descartes. In the 1630s, Descartes visited the royal gardens at Versailles, which were known for their intricate automata. When water was made to flow, music sounded, sea nymphs began to plove, and a giant Neptune, complete with trident, advanced Menac. Ingly whether the idea was in his mind before this visit or at the time of Newton's discoveries. The pouty of the Chinchillreldi had been challenged bv Martin Luther. Newton himself was a pious precise, and the specific argument of the Chinch was not with empirical method but with the theological conclusions that were being developed from Newton's ideas. See on clue. Science, which involved the concept of God as Creator and the central position of man in creation. Einstein doesn't like it/23. Not Descartes' philosophy, which he supported with his mathematics, became that the universe and all of the things in it also were automata from Descartes' time to the beginning of this century, and perhaps because of him, our ancestors began to see the universe as a great machine. Over the next 300 years they developed science specifically to discover how the great machine worked. Newton's second great contribution to science was his law of gravity. Gravity is a remarkable phenomenon, even though we take it for granted. For example, if we hold a ball off the ground, and then release it, the ball falls straight down to the ground. But how did that happen? The ground did not reach up and pull the ball down, yet the ball was pulled to the earth. The old physics called this unexplainable phenomenon action at a distance. Newton himself was as puzzled as any one. He wrote in his famous Philosophiae Naturae, Principia Mathematica, I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses. It is enough that gravity does really exist, and act according to the laws which we have explained, and abundantly serves to account for all the motions of the celestial bodies. For Newton clearly felt that a true understanding of the nature of gravity was beyond comprehension. In a letter to Richard Bentel, the classical scholar, he wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that, I believe, no man who has philosophic matters a competent fatuity of thinking could ever fall. In short, action at a distance could be described, but it could not be explained. Newton's thesis was that the same force which pulls apples downward also keeps the moon in orbit around the Earth and the planets in orbit around the Sun. To test his idea, he calculated various movements of the moon and the planets. Using his own mathematics, then he compared his findings 24/WLP with the observations of astronomers. His calculations and their observations matched in one stroke. Newton set aside the assumption of an essential difference between earthly and heavenly objects by showing that both of them are governed by the same laws. He established a rational celestial mechanics. What had been the purview of the gods, or God, came now within the comprehension of mortals. Newton's gravitational law does not explain gravity, that was done by Einstein in his general theory of relativity, but it does subject the effects of gravity to a rigorous mathematical formalism. Newton was the first person to discover principles in nature which unify large tracts of experience. He abstracted certain unifying concepts from the endless diversity of nature and gave those concepts mathematical expression. Because of this, more than anything else, Newton's work has influenced us so forcefully. Newton showed us that the phenomena of the universe are structured in rationally comprehensible ways. He gave us the most powerful tool in history. In the West we have used this tool, if not wisely, certainly to the best of our ability. The results, both positive and negative, have been spectacular. The story of our enormous impact on our environment begins with the work of Newton. It was Galileo Galilei who, following the Middle Ages, first quantified the physical world. He measured the motion, frequency, velocity, and duration of everything from falling stones to swinging pendulums, like the chandelier in his cathedral. It was René Descartes who developed many of the fundamental techniques of modern mathematics and gave us the picture of the universe as a great machine. It was Isaac Newton who formulated the laws by which the great machine runs. These men struck boldly against the grip of scholasticism, the medieval thought system of the 12th to the 15th centuries. They attempted to place man at the center of the stage, or at least back on the stage, to prove to him that he need not be a bystander in a world governed by unfathomable forces. It is perhaps the greatest irony of history that they accomplished just the opposite. Joseph Weizenbaum, a scientist at the Massachusetts Institute of Technology, wrote, in reference to computers, "Science promised man power, but, as so often happens when people are seduced by promises of power, the Einstein doesn't like it/25. Price is servitude and impotence. Power is nothing if it is not the power to choose. 6. How did this happen? Newton's laws of motion describe what happens to a moving object. Once we know the laws of motion, we can predict the future of a moving object, provided that we know certain things about it initially. The more initial information that we have, the more accurate our predictions will be. We also can predict backward in time, the past history of a given object. For example, if we know the present position and velocity of the Earth, the Moon and the Sun, we can predict where the Earth will be in relation to the Moon and the Sun at any particular time in the future, giving us a foreknowledge of eclipses, seasons and so on. In like manner, we can calculate where the Earth has been in relation to the Moon and the Sun, and when similar phenomena occurred in the past. Without Newtonian physics, the space program would not be possible. Moon probes are launched at the precise moment when the launch site on the Earth, which simultaneously is rotating around its axis and moving forward through space, is in a position relative to the landing zone on the Moon, which also is rotating and moving, such that the path traversed by the spacecraft is the shortest possible. The calculations of the Earth, Moon, and spacecraft movements are done by computer, but the mechanics used are the same ones that are described in Newton's Philosophiae Naturae Principia Mathematica. In practice, it is very difficult to know all the initial circumstances pertaining to an event. Even a simple action such as bouncing a ball off a wall is surprisingly complex. The shape, size, elasticity and momentum of the ball, the angle at which it was thrown, the density, pressure, humidity, and temperature of the air, the shape, hardness and position of the wall, to name a few of the essential elements, are all required to know where and when the ball will land. It is increasingly difficult to obtain all of the data necessary for accurate predictions. When more complex actions are involved according to the old physics, however, it is possible, in principle, to predict exactly how a given event is going to unfold if we have enough information about it. In practice, it is only the enormity of the task that prevents us from accomplishing it. 26/Woolley. The ability to predict the future based on a knowledge of the present and the laws of motion gave our ancestors a power they had never known. However, these concepts carry within them a very dispiriting logic. If the laws of nature determine the future of an event, then, given enough information, we could have predicted our present at some time in the past. That time in the past also could have been predicted at a time still earlier. In short, if we are to accept the mechanistic determination of Newtonian physics, if the universe really is a great machine, then from the moment that the universe was created and set into motion, everything that was to happen in it already was determined. According to this philosophy, we may seem to have a will of our own and the ability to alter the course of events in our lives, but we do not. Everything, from the beginning of time, has been predetermined, including our illusion of having a free will. The universe is a pre-recorded tape playing itself out in the only way that it can. The status of men is immeasurably more dismal than it was before the advent of science. The great machine runs blindly on, and all things in it are but cogs. According to quantum mechanics, however, it is not possible, even in principle, to know enough about the present to make a complete prediction about the future. Even if we have the time and the determination, it is not possible. Even if we have the best possible measuring devices, it is not possible. It is not a matter of the size of the task or the inefficiency of detectors. The very nature of things is such that we must choose which aspect of them we wish to know best, for we can know on one of them with precision. As Niels Bohr, another founder of quantum mechanics, put it, in quantum mechanics, we are not dealing with an arbitrary renunciation of a more detailed analysis of atomic phenomena, but with a recognition that such an analysis Is Tn principle excluded 7, italics in the original. For example, imagine an object moving through space. It has both a position and a momentum which we can measure. This is an example of the old, Newtonian, physics, moment. Tum is a combination of how big an object is, how fast it is going and the direction that it is moving, since we can. Einstein doesn't like it/27. Determine both the position and the momentum of the object. At a particular time, it is not a very difficult affair to calculate where it will be at some point in the future. If we see an airplane flying north at 200 miles per hour, we know that in 1 hour it will be 200 miles farther north if it does not change its course or speed. The mind-expanding discovery of quantum mechanics is that Newtonian physics does not apply to subatomic phenomena. In the subatomic realm, we cannot know both the position and the momentum of a particle with absolute precision. We can know both, approximately, but the more we know about one, the less we know about the other. We can know either of them precisely, but in that case, we can know nothing about the other. This is Werner Heisenberg's uncertainty principle. As incredible as it seems, it has been verified repeatedly by experiment. Of course, if we picture a moving particle, it is very difficult to imagine not being able to measure both its position and momentum. Not to be able to do so defies our common sense. This is not the only quantum mechanical phenomenon which contradicts common sense. Common sense contradictions, in fact, are the heart of the new physics. THEV tell us again and again that the world may not be what we think it is. It may be much, much more. Since we cannot determine both the position and momentum of subatomic particles, we cannot predict much about them. Accordingly, quantum mechanics does not and cannot predict specific events. It does, however, predict probabilities. Probabilities are the odds that something is going to happen, or that it is not going to happen. Quantum theory can predict the probability of a microscopic event with the same precision that Newtonian physics can predict the actual occurrence of a macroscopic event. Newtonian physics says, if such and such is the case now, then such and such is going to happen next. Quantum mechanics says, if such and such is the case now, then the probability that such and such is going to happen next is whatever it is calculated to be. We never can know with certainty what will happen to the particle that we are observing. All that we can know for sure are the probabilities for it to behave in certain ways. This is the most that we can know, because the two data which must be included in a Newtonian calculation, position and momentum, cannot both be known. 28/WW. With precision we must choose, by the selection of our experiment, which one we want to measure most accurately. The lesson of Newtonian physics is that the universe is governed by laws that are susceptible to rational understanding. By applying these laws we extend our knowledge of, and therefore our influence over, our environment. Newton was a religious person. He saw his laws as manifestations of God's perfection. Nonetheless, Newton's laws served man's cause well. They enhanced his dignity and vindicated his importance in the universe. Following the Middle Ages, the new field of science, natural philosophy, came like a fresh breeze to revitar /e the spirit. It is ironic that, in the end, natural philosophy reduced the status of men to that of helpless cogs in a machine whose functioning had been preordained from the day of its creation. Contrary to Newtonian physics, quantum mechanics tells us that our knowledge of what governs events on the subatomic level is not nearly what we assumed it would be. It tells us that we cannot predict subatomic phenomena with any certainty, we only can predict their probabilities. Philosophically, however, the implications of quantum mechanics are psychedelic. Not only do we influence our reality, but, in some degree, we actually create it, because it is the nature of things that we can know either the momentum of a particle or its position, but not both. We must choose which of these two properties we want to determine metaphysically. This is very close to saying that we create certain properties because we choose to measure those properties. Said another way, it is possible that we create something that has position, for example, like a particle, because we are intent on determining position, and it is impossible to determine position without having something occupying the position that we want to determine. Quantum physicists ponder questions like, did a particle with momentum exist before we conducted an experiment to measure its momentum? Did a particle with position exist before we conducted an experiment to measure its position? And did particles exist at all before we thought about them and measured them? Did we create the particles that we are experimenting with? Incredible as it sounds, this is a possibility that many physicists recognize. John Wheeler, a well-known physicist at Palmerston, wrote, Einstein doesn't like it/29. May the universe in some strange sense be brought into being by the participation of those who participate. The vital act is the act of participation. Participator is the incontrovertible new concept given by quantum mechanics. It strikes down the term observer of classical theory, the man who stands safely behind the thick glass wall and watches what goes on without taking part. It can't be done, quantum mechanics says. 8. The languages of Eastern mystics and Western physicists are becoming very similar. Newtonian physics and quantum mechanics are partners in a double irony. Newtonian physics is based upon the idea of laws which govern phenomena and the power inherent in understanding them, but it leads to impotence in the face of a great machine which is the universe. Quantum mechanics is based upon the idea of minimal knowledge of future phenomena. We are limited to knowing probabilities, but it leads to the possibility that our reality is what we choose to make it. There is another fundamental difference between the old physics and the new physics. The old physics assumes that there is an external world which exists apart from us. It further assumes that we can observe, measure and speculate about the external world without changing it. According to the old physics, the external world is indifferent to us and to our needs. Galileo's historical stature stems from his tireless and successful efforts to quantify, measure, the phenomena of the external world. There is great power inherent in the process of quantification. For example, once a relationship is discovered, like the rate of acceleration of a falling object, it matters not who drops the object, what object is dropped, or where the dropping takes place. The results are always the same. An experimenter in Italy gets the same results as a Russian experimenter who repeats the experiment a century later. The results are the same whether the experiment is done by a skeptic, a believer, or a curious bystander. Facts like these convinced philosophers that the physical Universe goes unheeded on its way doing what it must. Without regard for its inhabitants. For example, if we simultaneously drop two people from the same height, it is a verifiable 30/Woolley repeatable fact that they both will hit the ground at the same time, regardless of their weights. We can measure their fall, acceleration, and impact the same way that we measure the fall, acceleration and impact of stones. In fact, the results will be the same as if they were stones. But there is a difference between people and stones. You might say stones have no opinions or emotions. People have both. One of these dropped people, for example, might be frightened by his experience and the other might be angry. Don't their feelings have any importance in this scheme? No, the feelings of our subjects matter not in the least. When we take them up the tower again, struggling this time, and drop them off again, THEV fall with the same acceleration and duration that THEV did the first time, even though now, of course, they are both fighting mad. The great machine is impersonal. In fact, it was precisely this impersonality that inspired scientists to strive for absolute objectivity. The concept of scientific objectivity rests upon the assumption of an external world which is out there as opposed to an I, which is in here. This way of perceiving, which puts other people out there, makes it very lonely in here. According to this view, nature, in all her diversity, is out there. The task of the scientist is to observe the out there as objectively as possible. To observe something objectively means to see it as it would appear to an observer who has no prejudices about what he observes. The problem that went unnoticed for 3 centuries is that a person who carries such an attitude certainly is prejudiced. His prejudice is to be objective, that is, to be without a preformed opinion. In fact, it is impossible to be without an opinion. An opinion is a point of view. The point of view that we can be without a point of view is a point of view. The decision itself to study one segment of reality instead of an other is a subjective expression of the researcher who makes it. It affects his perceptions of reality, if nothing else. Since reality is what we are studying, the matter gets very sticky. Here, the new physics, quantum mechanics, tells us clearly that it is not possible to observe reality without changing it. If we observe a certain particle collision experiment, not only do we have no way of proving that the result would have been the same if we had not been watching it, all that we know indicates that it would not have been the same, because the result Einstein doesn't like it/31 that we got was affected by the fact that we were looking for it. Some experiments show that light is wave-like. Other experiments show equally well that light is particle-like. If we want to demonstrate that light is a particle-like phenomenon, or that light is a wave-like phenomenon, we only need to select the appropriate experiment. According to quantum mechanics, there is no such thing as objective/ITV. We cannot eliminate ourselves from the picture. We are a part of nature, and when we study nature there is no way around the fact that nature is studying itself. Physics has become a branch of psychology, or perhaps the other way round. Carl Jung, the Swiss psychologist, Wyatt, the PS/ecological rule says that when an inner situation is not made conscious, it happens outside, as fate, that is to save, when the individual remains undivided and does not become conscious of his inner contradictions, the world must perforce act out the conflict and be torn into opposite halves. 9. Jung's friend, the Nobel Prize-winning physicist, Wolfgang Paul, put it this way. From an inner center the pskshia seems to move out ward, in the sense of an extraversion into the physical world. 10. If these men are correct, then physics is the study of the structure of consciousness. The descent downward from the macroscopic level to the microscopic level, which we have been calling the realm of the very small, is a two-step process. The first step downward is to the atomic level, the second step downward is to the subatomic level. The smallest object that we can see, even under a microscope, contains millions of atoms. To see the atoms in a baseball, we would have to make the baseball the size of the eighth. If a baseball were the psi/e of the Earth, its atoms would be about the psi/e of grapes. If thou can picture the Earth as a huge glass ball filled with gaiapace, that is approximate how a baseball full of atoms would look. 32/Woolley. The step downward from the atomic level takes us to the subatomic level. Here we find the particles that make up atoms. The difference between the atomic level and the subatomic level is as great as the difference between the atomic level and the world of sticks and rocks. It would be impossible to see the nucleus of an atom the size of a grape. In fact, it would be impossible to see the nucleus of an atom the size of a room. To see the nucleus of an atom, the atom would have to be as high as a 14th of building. The nucleus of an atom as high as a 14-story building would be about the size of a gram of salt, since a nuclear particle has about 2,000 times more mass than an electron. The electrons revolving around this nucleus would be about as massive as dust particles. The dome of St. Peter's Basilica in the Vatican has a diameter of about 14 stories. Imagine a grain of salt in the middle of the dome of St. Peter's with a few dust particles revolving around it at the outer edges of the dome. This gives us the scale of subatomic particles. It is in this realm, the subatomic realm, that Newtonian physics has proven inadequate, and that quantum mechanics is required to explain particle behavior. A subatomic particle is not a particle like a dust particle. There is more than a difference in size between a dust particle and a subatomic particle. A dust particle is a thing, an object. A subatomic particle cannot be pictured as a thing. Therefore we must abandon the idea of a subatomic particle as an object. Quantum mechanics vs subatomic particles as tendencies to exist or tendencies to happen. How strong these tendencies are is expressed in terms of probabilities. A subatomic particle is a quantum, which means a quantity of something. What that something is, however, is a matter of speculation. Physicists feel that it is not meaningful even to pose the question. It may be that the search for the ultimate stuff of the universe is a crusade for an illusion. At the subatomic level, mass and energy change unceasingly into each other. Particle physicists are so familiar with the phenomena of mass becoming energy and energy becoming mass that they routinely measure the mass of particles in energy units *, since the tendencies of subatomic phenomena to be strictly speaking mass according to M's special theory of relativity. Energy and energy is mass. Where there is one, there v, the other. Einstein doesn't like it/33. Come manifest under certain conditions are probabilities. This brings us to the matter, no pun, of statistics. because there are millions of subatomic particles. In the smallest space that we can see, it is convenient to deal with them statistically. Statistical descriptions are pictures of crowd behavior. Statistics cannot tell us how one individual in a crowd will behave, but they can give us a fair accurate description, based on repeated observations, of how a group as a whole behaves. For example, a statistical study of population growth may tell us how many children were Rn in each of several years, and how many are predicted to be born in years to come. However, the statistics cannot tell us which families will have the new children and which ones will not. If we want to know the behavior of traffic at an intersection, we can install devices there to gather data. The statistics that these devices provide may tell us how many cars, for instance, turn left during certain hours, but not which cars. Statistics is used in Newtonian physics. It is used, for example, to explain the relationship between gas volume and pressure. This relation is named Boyle's law after its discoverer, Robert Boyle, who lived in Newton's time. It could as easily be known as the bicycle pump law, as we shall see. Boyle's law says that if the volume of a container holding a given amount of gas at a constant temperature is reduced by 1/2, the pressure exerted by the gas in the container doubles. Imagine a person with a bicycle pump. He has pulled the plunger fully upward, and is about ready to push it down. The hose of the pump is connected to a pressure gauge instead of to a big cool tire, so that we can see how much pressure is in the pump. Since there is no pressure on the plunger, there is no pressure in the pump cylinder and the gauge reads 0. However, the pressure inside the pump is not actually 0. We h/c at the bottom of an ocean of air, our atmosphere. The weight of the several miles of air above us exerts a pressure at sea level of 14.7 pounds on every square inch of our bodies. Our bodies do not collapse because they are exerting 14.7 pounds per square inch outward. This is the state that we usually read as /arrow on a bicycle pressure gauge to be accurate. Suppose that we set our gauge to read 14.7 pounds per square inch before we push down on the pump handle. Now we push the piston down half while the interior volume, 34 lp, of the pump cylinder is now 1/2 of its original size, and no air has been allowed to escape, because the hose is connected to a pressure gauge. The gauge now reads 29.4 pounds per square inch, or twice the original pressure. Next, we push the plunger 2/3 of the way down. The interior volume of the pump cylinder is now 1/3 of its original size, and the pressure gauge reads 3 tunes the original pressure, 44.1 pounds per square inch. This is Boyle's law. At a constant temperature, the pressure of a quantity of gas is inversely proportional to its volume. If the volume is reduced to 1/2, the pressure doubles. If the volume is reduced to 1/3, the pressure triple, etc. To explain why this is so, we come to classical statistics. The air, a gas, in our pump is composed of millions of molecules. Molecules are made of atoms. These molecules are in constant motion, and at any given time, millions of them are banging into the pump walls. Although we do not detect each single collision, the macroscopic effect of these millions of impacts on a square inch of the pump wall produces the phenomenon of pressure on it. If we reduce the volume of the pump cylinder by 1/2, we crowd the gas molecules into a space twice as small as the original one, thereby causing twice as many impacts on the same square inch of pump wall. The macroscopic effect of this is a doubling of the pressure. By crowding the molecules into 1/3 of the original space, we cause 3 times as many molecules to bang into the same square inch of pump wall, and the pressure on it triples. This is the kinetic theory of gases. In other words, pressure results from the group behavior of a large number of molecules in motion. It is a collection of individual events. Each individual event can be analyzed because, according to Newtonian physics, each individual event is theoretically subject to deterministic laws. In principle, we can calculate the path of each molecule in the pump chamber. This is how statistics is used in the old physics. Quantum mechanics also uses statistics, but there is a very big difference between quantum mechanics and Newtonian physics. In quantum mechanics, there is no way to predict individual events. This is the startling lesson that experiments in the subatomic realm have taught us. Therefore, quantum mechanics concerns itself only with group behavior. It intentionally leaves vague the relation between group behavior and individual events because Einstein doesn't like it/35. All subatomic events cannot be determined accurately, the uncertainty principle, and, as we shall see in high-energy particles, they constantly are changing. Quantum physics abandons the laws which govern individual events and states directly the statistical laws which govern collections of events. Quantum mechanics can tell us how a group of particles will behave/e, but the only thing that it can say about an individual particle is how it probably will behave. Probability is one of the major characteristics of quantum mechanics. This makes quantum mechanics an ideal tool for dealing with subatomic phenomena. For example, take the phenomenon of common radioactive decay, luminous watch dials. Radioactive decay is a phenomenon of predictable overall behavior consisting of unpredictable individual events. Suppose that we put 1 gram of radium in a time vault and leave it there for 1600 years. When we return, do we find 1 gram of radium? No, we find only half a gram. This is because radium atoms naturally disintegrate at a rate such that every 1600 years half of them are gone. Therefore, physicists say that radium has a half-life of 1600 years. If we put the radium back in the vault for another 1600 years, only 1/4 of the original gram would remain. When we opened the vault again every 1600 years, 1/2 of all the radium atoms in the world disappear. How do we know which radium atoms are going to disintegrate and which radium atoms are not going to disintegrate? We don't. We can predict how many atoms in a piece of radium are going to disintegrate in the next hour, but we have no way of determining which ones are going to disintegrate. There is no physical law that we know of which governs this selection. Which atoms decay is purely a matter of chance. Nonetheless, radium continues to decay, on schedule as it were, with a precise and unvarying half-life of 1600 years. Quantum theory dispenses with the laws governing the disintegration of individual radium atoms and proceeds directly to the statistical laws governing the disintegration of radium atoms as a group. This is how statistics is used in the new physics. Another good example of predictable overall, statistical behavior consisting of unpredictable individual events is the constant variation of intensity among spectral lines. Remember that, according to Bohr's theory, the electrons of an atom. 36/WLP are located only in shells which are specific distances from the nucleus, page 12. Normally, the single electron of a hydrogen atom remains in the shell closest to the nucleus, the ground state. If we excite it, add energy to it, we cause it to jump to a shell farther out. The more energy we give it, the farther out it jumps. If we stop exciting it, the electron jumps inward to a shell closer to the nucleus, eventually returning all the wav to the innermost shell. With each jump from an outer shell to an inner shell, the electron emits an energy amount equal to the energy amount that it absorbed when we caused it to jump outward. These emitted energy packets, photons, constitute the light which, when dispersed through a prism, forms the spectrum of 100 or so colored lines that is peculiar to hydrogen. Each colored line in the hydrogen spectrum is made from the light emitted from hydrogen electrons as they jump from a particular outer shell to a particular inner shell. What we did not mention earlier is that some of the lines in the hydrogen spectrum are more pronounced than others. The lines that are more pronounced are always more pronounced, and the lines that are faint are always faint. The intensity of the lines in the hydrogen spectrum varies because hydrogen electrons returning to the ground state do not always take the same route. Shell 5, for example, may be a more popular stopover than shell 3. In that case, the spectrum produced by millions of excited hydrogen atoms will show a more pronounced spectral line corresponding to electron jumps from shell 5 to shell 1, and a less pronounced spectral line corresponding to electron jumps from, say, shell 3 to shell 1. That is because, in this example, more electrons stop over at shell 5 before jumping to shell 1 than stop over at shell 3 before jumping to shell 1. In other words, the probability is very high, in this example, that the electrons of excited hydrogen atoms will stop at shell 5 on their way back to shell 1, and the probability is lower that they will stop at shell 3. Said another way, we know that a certain number of electrons probably will stop at shell 5 and that a certain lesser number of electrons probably will stop at shell 3. Still, we have no way of knowing which electrons will stop, whereas before, we can describe precisely an overall behavior without being able to predict a single one of the individual events which comprise it. Einstein doesn't like it/37. This brings us to the central philosophical issue of quantum mechanics, namely, what is it that quantum mechanics describes? Put another way, quantum mechanics statistically describes the overall behavior and or predicts the probabilities of the individual behavior of what? In the autumn of 1927, physicists working with the new physics met in Brussels, Belgium, to ask themselves this question. Among others, what they decided there became known as the Copenhagen interpretation of quantum mechanics *. Other interpretations developed later, but the Copenhagen interpretation marks the emergence of the new physics as a consistent way of viewing the world. It is still the most prevalent interpretation of the mathematical formalism of quantum mechanics. The upheaval in physics following the discovery of the inadequacies of Newtonian physics was all but complete. The question among the physicists at Brussels was not whether Newtonian mechanics could be adapted to subatomic phenomena. It was clear that it could not be, but rather, what was to replace it. The Copenhagen interpretation was the first consistent formulation of quantum mechanics. Einstein opposed it in 1927. And he argued against it until his death, although he, like all physicists, was forced to acknowledge its advantages in explaining subatomic phenomena. The Copenhagen interpretation says, in effect, that it does not matter what quantum mechanics is about. The important thing is that it works in all possible experimental situations. This is one of the most important statements in the history of science. The Copenhagen interpretation of quantum mechanics began a monumental reunion which was all but unnoticed. At the time, the rational part of our psyche, typified by science, began to merge again with that other part of us which we had ignored since the 1700s, our irrational side. The scientific idea of truth traditionally had been anchored in an absolute truth somewhere out there, that is, an absolute truth with an independent existence. The closer that we came in our approximations to the absolute truth, the truer. This was the Fifth Solvay Congress at which Bohr and Einstein conducted their now famous debates. The term Copenhagen interpretation reflects the dominant influence of Niels Bohr, from Copenhagen, and his school of thought. The Copenhagen interpretation says that quantum theory is about correlations in our experiences. It is about what will be observed under specified conditions. 38/WLP. Our theories were said to be, although we might never be able to perceive the absolute truth directly, or to open the watch, as Einstein put it, still we tried to construct theories such that for every facet of absolute truth, there was a corresponding element in our theories. The Copenhagen interpretation does away with this idea of a one-to-one correspondence between reality and theory. This is another way of saying what we have said before. Quantum mechanics discards the laws governing individual events and states directly the laws governing aggregations. It is very pragmatic. The philosophy of pragmatism goes something like this. The mind is such that it deals only with ideas. It is not possible for the mind to relate to anything other than ideas. Therefore, it is not correct to think that the mind actually can ponder reality. All that the mind can ponder is its ideas about reality. Whether or not that is the way reality actually is a meta-physical issue. Therefore, whether or not something is true is not a matter of how closely it corresponds to the absolute truth, but of how consistent it is with our experience. The extraordinary importance of the Copenhagen interpretation lies in the fact that for the first time, scientists attempting to formulate a consistent physics were forced by their own findings to acknowledge that a complete understanding of reality lies beyond the capabilities of rational thought. It was this that Einstein could not accept. The most incomprehensible thing about the world, he wrote, is that it is comprehensible, but the deed was done. The new physics was based not upon absolute truth but upon us. Henry Pierce Stapp, a physicist at the Lawrence Berkeley Laboratory, expressed this eloquently. The philosophy of pragmatism was cited by the American psychologist William James recently. The pragmatic aspects of the Copenhagen interpretation of quantum mechanics have been emphasized. Henry Pierce Stapp, theoretical physicist at the Lawrence Berkeley Laboratory in Berkeley, California. The Copenhagen interpretation, in addition to the pragmatic part, has the claim that quantum theory is in some sense complete, that no theory can Explain subatomic phenomena in any more detail. An essential feature of the Copenhagen interpretation is the high estimate of complementarity, to be discussed later. Some historians practically equate the Copenhagen interpretation and complementarity. Complementarity is summed in a genial way in Stapp's pragmatic interpretation all quantum me. But the special emphasis on complementarity is characteristic of the Copenhagen interpretation. Einslindolsent /_t/50. The Copenhagen interpretation of quantum mechanics was essentially a rejection of the presumption that nature could be understood in terms of elementary space-time realities. According to the new view, the complete description of nature at the atomic level was given BV probability functions that referred not to underlying microscopic space-time realities but rather to the macroscopic objects of sense experience. The theoretical structure did not extend down and anchor itself on fundamental microscopic space-time realities. Instead, it turned back and anchored itself in the concrete sense realities that form the basis of social life. This pragmatic description is to be contrasted with descriptions that attempt to peer behind the scenes and tell us what is really happening. 12. Another way of understanding the Copenhagen interpretation, in retrospect, is in terms of split brain analysis. The human brain is divided into two halves which are connected at the center of the cerebral cavity by a tissue to treat certain conditions, such as epilepsy. The two halves of the brain sometimes are separated surgically from the experiences reported by and the observations made of persons who have undergone this surgery. We have discovered a remarkable fact. Generally speaking, the left side of our brain functions in a different manner than the right side. Each of our two brains sees the world in a different way. The left side of our brain perceives the world in a linear manner. It tends to organize sensory input into the form of points on a line, with some points coming before others. For example, language, which is linear, the words which you are reading flow along a line from left to right, is a function of the left hemisphere. The left hemisphere functions logically and rationally. It is the left side of the brain which creates the concept of causality, the image that one thing causes another, because it always precedes it. The right hemisphere, by comparison, perceives whole patterns. Persons who have had split brain operations actually have two separate brains. When each hemisphere is tested separately, it is found that the left brain remembers how to speak and use words, while the right brain generally cannot. However, the right brain remembers the lyrics of songs. The left side of our brain tends to ask certain questions of its sensory 40/Woolley input. The right side of our brain tends to accept what it is given more freely. Roughly speaking, the left hemisphere is rational and the right hemisphere is irrational. 13. Physiologically, the left hemisphere controls the right side of the body and the right hemisphere controls the left side of the body. In view of this, it is no coincidence that both literature and mythology associate the right-left hemisphere with rational, male, and assertive characteristics, and the left-hand, right hemisphere, with mystical, female, and receptive characteristics. The Chinese wrote about the same phenomena thousands of years ago, yin and yang, although they were not known for their split brain surgery. Our entire society reflects a left hemispheric bias. It is ratio Now, masculine and assertive, it gives very little reinforce. Meant to those characteristics representative of the right hemisphere, intuitive, feminine, and receptive, the advent of science marks the beginning of the ascent of left hemispheric thinking into the dominant mode of Western cognition and the descent of right hemispheric thinking into the underground underpsych status from which it did not emerge, with scientific recognition, until Freud's discovery of the unconscious which, of course, he labeled dark, mysterious and irrational, because that is how the left hemisphere / the right hemisphere. The Copenhagen interpretation was, in effect, a recognition of the limitations of left hemispheric thought, although the PhDists at Brussels in 1927 could not have thought in those terms. It was also a reopenfu, of those psychic aspects which long had been ignored in a rationalistic society. After all, physicists are essentially people who wonder at the universe. To stand in awe and wonder is to understand in a / specific way. Even if that understanding cannot be described, the subjective experience of wonder is a message to the rational mind that the object of wonder is being perceived / and understood in ways other than the rational. The next time you are awed by something, let the feeling flow freely through you and do not try to understand it. You will find that you do understand, but in a way that you will not be able to put into words. You are perceiving intuitively. Your right hemisphere, it has not atrophied from lack of use, but our skill in listening to it has been dulled by 3 centuries of neglect. Einstein doesn't like it /41. Woolly masters perceive in both ways, the rational and the irrational, the assertive and the receptive, the masculine and the feminine. They reject neither one nor the other. Only dance. Dancing Lesson 4. Newtonian physics. Can picture it. Based on ordinary sense perceptions. Describes things, individual objects in space and their changes in time. Predicts events. Assumes an objective reality. Out there, we can observe something without changing it. Claims to be based on absolute truth, the way that nature really is behind the scenes. Dancing Lesson 4. Quantum mechanics. Cannot picture it. Based on behavior of sub-atomic particles and systems. Not directly observable. Describe one statistical behavior of Syst J. Predicts probabilities. Does not assume an objective reality apart from our experience. We cannot observe some thing without changing it. Claims only to correlate experience correctly. This is quantum mechanics. The next question is, does it work? 1. How? L. Part 1. Patterns of organic energy. Chapter 1. Living. When we talk of physics as patterns of organic energy, the word that catches our attention is organic. Organic means living. Most people think that physics is about things that are not living, such as pendulums and billiard balls. This is a common point of view, even among physicists, but it is not as evident as it may seem. Let us explore this viewpoint with the aid of a hypothetical person, a young man named Jim DeWitt, who is the perpetual champion of the non-obvious. It is not at all true, says Jim DeWitt, that physics is about non-living things. This is evident from our discussion of falling bodies, page 29. Even if some of them are the human kind, they all accelerate at the same rate in a vacuum. So physics does apply to living things. But that is an unfair example, we say. Rocks have no choice in the matter of falling. If we drop them, they fall. If we don't drop them, they don't fall. Humans, on the other hand, exercise choice. Accidents excluded, humans ordinarily are not found in the act of falling. Why? Because they know that falling may hurt them and they have no desire to be hurt. In other words, humans process information, they know that they may be hurt, and they respond to it by not falling. Rocks can do neither. That is the way things appear, says DeWitt, but it may not be the way they actually are. For example, by watching time-lapse photography we know that plants often respond to stimuli with human-like reactions. They retreat from pain. 45. 46 / patterns of organic energy advance toward pleasure, and even languish in the absence of affection. The only difference is that they do it at a much slower rate than we do. So much slower, in fact, that it appears to the ordinary perception that they do not react at all. If this is so, then how can we say with certainty that rocks and even mountain ranges do not react also as living organisms, but with a reaction time so slow that to catch it with time-lapse photography would require millennia between exposures? Of course, there is no way to prove this, but there is no way of disproving it either. The distinction between living and non-living is not so easy to make. That's clever, we think, but from a practical point of view, it cannot be observed that inert matter responds to stimuli. And there is no question that humans do. Wrong again, says DeWitt, reading our thoughts. Any chemist can verify that most chemicals, which usually come out of the ground as rocks, do react to stimulation. Under the right conditions, for example, sodium reacts to chlorine by forming sodium chloride, salt. Iron reacts to oxygen by forming iron oxides, rust, and so on, just as humans react to food when they are hungry and to affection when they are lonely. Well, this is so, we admit, but it hardly seems fair to compare a chemical reaction to a human reaction. A chemical reaction either happens or it does not happen. There is nothing in between. When two such chemicals are combined properly, they react. If they are not properly combined, they do not react. Humans are much more complex. If we offer food to a hungry person, he might eat it or he might not, depending upon his circumstances, and if he eats, he might eat his fill or he might not. Consider the person who is hungry and late for an appointment. If the appointment is important enough, he will go without eating, even though he is hungry. If a person knows that his food is poisonous, he will not eat, even though he is hungry. It is a matter of processing information and responding appropriately that distinguishes a human reaction from a chemical reaction. Chemicals have no options, they always must act one way or the other. Of course, beams Jim DeWitt, but how do we know that our responses are not as rigidly pre-programmed as those of a chemical? with the only difference being that our programs are enormously more complex. We may not have any more freedom of action than stones do, although, unlike stones, we deceive ourselves into thinking that we do. Living /47. We have no way to dispute this argument. De Witt has shown us the arbitrary quality of our prejudices. We would like to think that we are different from stones because we are living and they are not, but there is no way we can prove our position or disprove his. We cannot establish clearly that we are different from inorganic substances. That means that, logically, we must admit that we may not be alive. Since this is absurd, the only alternative is to admit that inanimate objects may be living. The distinction between organic and inorganic is a conceptual prejudice. It becomes even harder to maintain as we advance into quantum mechanics. Something is organic, AC. According to our definition, if it can respond to processed information. The astounding discovery awaiting newcomers to physics is that the evidence gathered in the development of quantum mechanics indicates that subatomic particles constantly appear to be making decisions. More than that, the decisions they seem to make are based on decisions made elsewhere. Subatomic particles seem to know instantaneously what decisions are made elsewhere, and elsewhere can be as far away as another galaxy. The key word is instantaneously. How can a subatomic particle over here know what decision another particle over there has made at the same time the particle over there makes it? All the evidence belies the fact that quantum particles are actually particles. A particle, as we mentally picture it, classically defined, is a thing which is confined to a region in space. It is not spread out. It is either here or it is there, but it cannot be both here and there at the same time. A particle over here can communicate with a particle over there, by shouting at it, sending it a TV picture, waving, etc. But that takes time, even if only milliseconds. If the two particles are in different galaxies, it could take centuries for a particle here to know what is going on over there while it is happening. It must be over there. But if it is over there, it cannot be here. If it is both places at once, then it is no longer a particle. This means that particles may not be particles at all. Page 32. It also means that these apparent particles are related with other particles in a dynamic and intimate way that coincides with our definition of organic. Some biologists believe that a single plant cell carries within it the capability to reproduce the entire plant. Similarly, the 48 patterns of organic energy. Philosophical implication of quantum mechanics is that all of the things in our universe, including us, that appear to exist independently are actually parts of one all-encompassing organic pattern, and that no parts of that pattern are ever really separate from it or from each other. To understand these decisions and what makes them, let us start with a discovery made in 1900 by Max Planck. This year generally is considered the birthday of quantum mechanics. In December of that year, Planck reluctantly presented to the scientific community a paper which was to make him famous. He himself was displeased with the implications of his paper, and he hoped that his colleagues could do what he could not. do explain its contents in terms of Newtonian physics. He knew in his heart, however, that the could not, and that neither could anyone else. He also sensed and correct also that his paper would shift the vive foundations of science. What had Planck discovered that disturbed him so much? Planck had discovered that the basic structure of nature is granular, or, as physicists like to say, discontinuous. What is meant by discontinuous? 9. If we talk about the population of a city, it is evident that it can fluctuate only by a whole number of people. The least the population of a city can increase or decreases by 1 person. It cannot increase by 7 of a person. It can increase or decrease by 15 people, but not by 1527 people. In the dialect of pH 6, a population can change only in discrete increments, or discontinuously it can get larger or smaller only in jumps, and the smallest jump that it can make is a whole person. In general, this is what Planck discovered about the processes of nature. Planck did not intend to undermine the foundations of any /German physics. He was a conservative German physicist. Rather, he advertently fathered the revolution of quantum mechanics by attempting to solve a specific problem dealing with energy radiation. Planck was searching for an explanation of WHV things behave as they do when they get hot, namely, he wanted to know how objects glow brighter as they get hotter, and change color when the temperature is increased or decreased. Classical physics, which successfully had unified such diverse fields as acoustics, optics, and astronomy, which had all but satiated the scientific appetite, which had unraveled the enigmas living /49 of the universe and rearranged them in neat packages, held no sensible explanation of this commonplace phenomenon. It was, to use the parlance of the day, one of the few clouds on the horizon of classical physics. In 1900, physicists pictured the atom as a nucleus that looked something like a plum to which were attached tiny protruding springs. This was before the planetary model of the atom. At the end of each spring was an electron giving the atom a jolt. By heating it, for instance, caused its electrons to jiggle, oscillate, on the ends of their springs. The jiggling electrons were thought to give off radiant energy, and this was thought to account for the fact that hot objects glow. An accelerating electrical charge creates electromagnetic radiation. An electron carries an electrical charge, negative, and if it is jiggling, it is accelerating, first in one direction and then in the other. Physicists thought that heating the atoms in a metal caused them to become agitated, and this in turn caused their electrons to jiggle up and down and emit HGHF. In the process, the energy that the atom absorbed when it was jolted, heated, the theory was radiated BV. The jiggling electrons, you can substitute atomic oscillators if your friends won't take jiggling electrons snurself. This same theory also claimed that the energy absorbed BV an atom was distributed equal to its oscillators, electrons, and that those electrons which oscillated, jiggled, at higher frequencies, faster, radiated their energy most efficiently. Unfortunately, this theory didn't work. It proved some very incorrect things. First, it proved that all heated objects emit more high-frequency light, blue, violet, than low-frequency light, red. In other words, even moderately hot objects, AC, according to this classical theory, emit an intense blue-white color, just like objects which are white hot but in lesser amounts. This is incorrect. Moderately hot objects emit primarily red light. Second, the classical theory proved that highly heated objects radiate infinite amounts of high-frequency light. This is incorrect. Highly heated objects emit a finite amount of high-frequency light. Do not be concerned with high frequencies and low frequencies. These terms will be explained shortly. The point is that Planck was exploring one of the last major problems of classical physics, its erroneous predictions concerning energy. Radiation physicists dubbed this problem the ultraviolet catastrophe. Although it sounds like a rock band, the ultra 50 patterns of organic energy violet catastrophe reflected a real concern with the fact that heated objects do not radiate large amounts of energy in the form of ultraviolet light, the highest frequency light known in 1900, the way the classical theory predicted. The name of the phenomenon that Planck was studying is blackbody radiation. Blackbody radiation is the radiation that comes from a non-reflecting, perfectly absorbing flat, non-glossy black body. Since black is the absence of color, no light is reflected or emitted. Black bodies have no color unless we heat them. If a black body is glowing a certain color, we know that it is because of the energy that we have added to it, and not because it reflects or emits that color spontaneously. A black body does not always mean a solid body that is black. Suppose that we have a metal box that is completely sealed except for a small hole. If we look inside, what do we see? Nothing, because there is no light in there. A little light may come in through the hole, but not that much. Now suppose that we heat the box until it glows red and then look through the hole. What do we see? Carrot red. Who said physics is hard? Carrot. This is the kind of phenomenon that Planck studied. All the physicists in 1900 assumed that after the electrons of an excited atom began to jiggle, they radiated their energy smoothly and continuously until they ran down and their energy was dissipated. Planck discovered that excited atomic oscillators do not do this. They emit and absorb energy only in specific amounts instead of radiating energy smoothly and continuously like a clock spring runs down. They radiate their energy in spurts, dropping to a lower energy level after each spurt until they stop oscillating altogether. In short, Planck discovered that the changes of nature are explosive, not continuous and smooth. Planck was the first physicist to talk about energy packets and quantized oscillators. He sensed that he had made a major discovery, one which ranked with the discoveries of Newton, and he was right. The philosophy and paradigms of physics never were to be the same, although it took another 27 years for quantum mechanics to take form. The hypothesis of quanta has led to the idea that there are changes in nature which do not occur continuously but in an explosive manner. Max Planck Neubauten der physikischen Erkenntnis 1913 Trans FD Alb. Philafog Vol 28 1914. Living. /51. It is difficult today to understand how bold was Planck's theory of quanta. Victor Guillem, professor of physics at Harvard, put it this way. Planck had to make a radical and seemingly absurd assumption, for according to classical laws, and common sense as well, it had been presumed that an electronic oscillator, once set in motion by a jolt, radiates its energy smoothly and gradually while its oscillator emotion subsides. To rest, Planck had to assume that the oscillator ejects its radiation in sudden spurts, dropping to lesser amplitudes of oscillation with each spurt. He had to postulate that the energy of motion of each oscillator can neither build up nor subside smoothly and gradually, but may change only in sudden jumps in a situation where energy is being transferred to and fro between the oscillators and the light waves. The oscillators must not only emit but also absorb radiant energy in discrete packets. He coined the name quanta for the packets of energy, and he spoke of the oscillators as being quantized. Thus, the trenchant concept of the quantum entered physical. Planck is not only the father of quantum mechanics, he also is the discoverer of Planck's constant. Planck's constant is a certain number which never changes. It is used to calculate the size of the energy packets, quanta, of each light frequency. Color, the energy in each light quantum of a particular color, is the frequency of the light multiplied by Planck's constant. All of the energy packets of each color have the same amount of energy. All of the energy packets of red light, for example, are the same psi/e. All of the energy packets of green light are the same psi/e. All of the energy packets of violet light are the same size. The energy packets of violet light, however, are larger than the energy packets of green light, and the energy packets of green light are larger than the energy packets of red light. In other words, Planck discovered that energy is absorbed and emitted in little chunks, and that the size of the chunks of a low-frequency light like red is smaller than the SU of the *h equals 663 x 10^2 trg sec. 52 / patterns of organic energy. Chunks of a high-frequency light, like violet. This explains why hot objects radiate energy as they do. When a black body is put over low heat, the first color it glows is red, because the energy packets of red light are the smallest energy packets in the visible light spectrum. As the heat is increased, more energy is available to shake loose bigger energy packets. The bigger energy packets make the higher frequency colors, such as blue and violet. Why does the glow of hot metal seem to increase steadily in brightness as the temperature increases? Because the tiny steps upward and downward in brightness are so incredibly small that our eyes cannot discern them. Therefore, on the large scale, or macroscopic level, this aspect of nature is not evident in the subatomic realm. However, it is the dominant characteristic of nature. If this discussion of emission and absorption of energy packets reminds you of Niels Bohr, page 12, thou art right. However, Bohr was not to arrive at his theory of specific electron orbits for another 13 years. By that time, physicists had discarded the plum-with-jigong electrons model of the atom in favor of the planetary model, in which electrons revolve around a nucleus. Between Planck's discovery of the quantum, 1900, and Bohr's analysis of the hydrogen spectrum, 1913, a brilliant physicist burst upon the scene with a force seldom exerted by an individual. His name was Albert Einstein. In 1 Ver, 1905, at 26. Einstein published 5 significant papers. 3 of them were pivotal in the development of physics, and, to a large extent, in the development of the West. The first of these 3 papers described the quantum nature of light. It won him a Nobel Prize in 1921. The second paper described molecular motion. The third paper set forth the special theory of relativity, which we will study later. T. Asterisk bar speculated th it electiomic orbits are arranged bv nature at unvarying specific distances from the nucleus of the atom, and that when they absorb energy the electrons in the atom jump outward from the orbit closest to the nucleus, the ground state of the atom, and eventually return to the nearest orbit in the process, emitting ntg/packets equal to the energy packets that they absorb in jumping outward by pi, opposed that when only a little energy is available, low heat, on of small energy packets are absorbed bv the electrons, and they do not jump out via far when THEV atom to then lowest energy level. They emit small energy packets like those of red light when more energy is available, high heat, larger NEG packets AIE available. The electrons make bigger jumps outward, and on returning they emit larger energy. Living /53. Einstein's theory of light was that it is composed of tiny particles. A beam of light, said Einstein, is analogous to a stream of bullets. Each bullet is called a photon. This is similar to what Planck proposed, but actually it is a leap beyond. Planck discovered that energy is absorbed and emitted in packets. He described the processes of energy absorption and emission. Einstein theorized that energy itself is quantized. To prove his theory, Einstein referred to a phenomenon I called the photoelectric effect. When light hits, impinges on the surface of a metal, it jars electrons loose from the atoms in the metal and sends them flying off with appropriate equipment. We can count these electrons and measure how fast they are traveling. Einstein's theory of the photoelectric effect was that each time one of the bullets, or photons, hits an electron, it knocks it away, just as one billiard ball hitting another billiard ball knocks it away. Einstein based his revolutionary theory on the experimental work of Philippe Lenard, who won the Nobel Prize in 1905. Lenard showed that the flow of electrons in the photoelectric effect begins immediately when the impinging light strikes the target metal. Turn on the light and out come the electrons. According to the wave theory of light, the electrons in a metal only start to jiggle when they are struck by light waves. They do not come out of the metal until they are moving fast enough. This takes several oscillations, like pumping a child's swing, higher and higher until it goes around the bar. In short, the wave theory of light predicts a delayed emission of electrons. Lenard's experiments showed a prompt emission of electrons. This prompt emission of electrons in the photoelectric effect is explained by Einstein's particle theory of light. Every time a particle of light, a photon, strikes an electron, it immediately knocks it out of its atom. Lenard also discovered that reducing the intensity of the impinging light beam, making it dimmer, did not reduce the velocity of the rebounding electrons, but it did reduce the number of the rebounding electrons. He found that the velocity packets like those of blue and violet light, therefore over low heat metal glows red, and over high heat it glows blue-white. Each of Einstein's major 1905 papers dealt with a fundamental physical constant H. Planck's constant, the photon hypothesis, K. Boltzmann's constant, the analysis of Brownian movement, and C. the velocity of light, the special theory of relativity. 54/patterns of organic energy of the rebounding electrons could be altered, however, by changing the color of the impinging light. This also was explained by Einstein's new theory. According to Einstein's theory, each photon of a given color, like green, for instance, has a certain amount of energy. Reducing the intensity of a beam of green light only reduces the number of photons in the beam. Each remaining photon, however, still has the same amount of energy as any other photon of green light. Therefore, when any photon of green light strikes an electron, it knocks it away with a certain amount of energy, which is characteristic of green light photons. Max Planck described Einstein's theory this way. The photons, the drops of energy, do not grow smaller as the energy of the ray grows less. What happens is that their magnitude remains unchanged and they follow each other at greater intervals. 2. Einstein's theory also substantiated Planck's revolutionary discovery. High-frequency light, like violet, is made of higher energy photons than low-frequency light, like red. Therefore, when violet light, which is made of high-energy photons, strikes an electron, it causes the electron to rebound with a high velocity. When red light, which is made of low-energy photons, strikes an electron, it causes the electron to rebound at a low velocity. In either case, increasing or decreasing the intensity of the light increases or decreases the number of rebounding electrons, but only by changing the color of the impinging light can we change their velocity. In short, Einstein demonstrated, using the photoelectric effect, that light is made of particles, or photons, and that the photons of high-frequency light have more energy than the photons of low-frequency light. This was a momentous achievement. The only problem was that 102 years earlier an Englishman named Thomas Young had shown that light is made of waves, and no one, including Einstein, was able to disprove him. Now we come to the matter, no pun, of waves. A particle is something that is contained in one place. A wave is something that is spread out. On the next page are some types of waves. Living /55. We are concerned only with the last type of wave. Here is a more detailed picture of it. A. Wavelength, FRJ. Direction of movement. A wavelength is the distance between one crest of a wave and the next. The longest radio waves are over 6 miles long. X-rays, on the other hand, are only about 1/1000th of a centimeter long. Visible light has wavelengths in the neighborhood of 4 to 8/100,000ths of a centimeter. The amplitude of a wave is the height of the wave crest above the dotted line. Here are 3 waves with different amplitudes. The one in the middle has the largest amplitude. 56 patterns of organic energy. The frequency of the wave tells us how many crests pass a given point, like pointer in the drawing, each second. If the wave is moving in the direction of the arrow and a crest passes pointer each second, the frequency of the wave is 1 cycle per second. If 10½ crests pass point every second, the frequency of the wave is 10.5 cycles per second. If 10,000 crests pass the same point every second, the frequency of the wave is 10,000 cycles per second. And so on. The velocity of the wave can be determined by multiplying the wavelength by the frequency. For example, if the wave length of a wave is 2 feet and the frequency of the wave is 1 cycle per second, the wave is moving one wavelength, 2 feet, every second. Therefore, its velocity is 2 feet per second. If the wavelength is 2 feet and the frequency is 3 cycles per second, the velocity of the wave is 6 feet per second because the wave moves 3 wavelengths forward every second. There is nothing complicated about this. We can determine how fast a man is running if we know the length of his stride, and how many of them he takes in a second. By multiplying them together we get how far the man runs in a second. If his stride is 3 feet and he takes 2 strides per second, then he runs 6 feet per second, about 4 miles per hour. We do the same things with waves, except that we use wavelengths instead of strides. Although the velocity of a light wave can be determined by multiplying its wavelength by its frequency, it is not necessary. Physicists have discovered that the velocity of light in empty space is always 186,000 miles per second. This applies to all electromagnetic waves, including light. Therefore, all light waves, blue ones, green ones, red ones, etc., have the same velocity as radio waves, X-rays, and all the other forms of electromagnetic radiation. The speed of light is a constant. It is represented by the letter c. The constant c is, approximately, 186,000 miles per second. And it never varies, which is what makes it a constant. It does not matter whether light is going up or down, has a high frequency or a low frequency, a large wavelength or a small wavelength, is coming toward us or going away from us, its velocity is always 186,000 miles per second. This fact led Albert Einstein to the theory of special relativity, as we shall see later. Living /57. It also permits us to know both the frequency and the wavelength of light if we know either one of them. This is because the product of the two is always 186,000 miles per second in empty space. The larger one of them is, the smaller the other must be. For example, if we know that by multiplying two numbers together we get 12 for an answer, and if we know that one of the numbers is 6, then we also know that the other number must be 2. If we know that one of the numbers is 3, then we know that the other number must be 4. Similarly, the higher the frequency of a light wave, the shorter its wavelength must be, the lower the frequency of a light wave, the longer its wavelength must be. In other words, high-frequency light has a short wavelength and low-frequency light has a long wavelength. Now we return to Planck's discovery. Planck discovered that the energy of a light quantum increases with frequency. The higher the frequency, the higher the energy. Energy is proportional to frequency, and Planck's constant is the constant of proportionality between them. This simple relation between frequency and energy is important. It is central to quantum mechanics. The higher the frequency, the higher the energy, the lower the frequency, the lower the energy. When we put wave mechanics and Planck's discovery together we get this: high-frequency light, such as violet light, has a short wavelength and high energy. Low-frequency light, such as red light, has a long wavelength and low energy. This explains the photoelectric effect. Photons of violet light knock electrons loose from the atoms of a metal and send them flying away at a higher velocity than photons of red light. Because the photons of violet light, which is a high-frequency light, have more energy than the photons of red light, which is a low-frequency light. This all makes sense if you overlook the fact that we are talking about particles, photons, in terms of waves, frequencies, and waves in terms of particles, which, of course, makes no sense at all. If you feel that you understand the last few pages, congratulations! You have mastered the most difficult mathematics in the book. If not, go back to page 54 and reread these pages. It is easy to dance with wavelengths and frequencies if you know how they are connected. Waves are playful creatures that like to do dances of their 58 patterns of organic energy own. For example, under certain conditions they bend around corners. When this happens it is called diffraction. Imagine that we are in a helicopter hovering over the mouth of an artificial harbor. The mouth of the harbor is wide enough for two aircraft carriers to pass each other going through it. The sea is rough and the wind and waves are blowing straight into the mouth of the harbor. When we look down, this is the pattern that we see the waves making in the harbor. The waves are stopped cleanly by the walls of the harbor, except at the harbor entrance, where they continue straight forward into the harbor until they are dissipated. Now imagine that the mouth of the harbor is so small that a rowboat scarcely can pass through it. As we look down from the helicopter, the pattern we see is quite different. Living /59. Instead of moving directly ahead into the harbor, the waves inside the harbor are spreading out from the mouth of the harbor almost as if it were a pond and we had dropped a rock into it at that point. This is diffraction. Why does it happen? Why does reducing the size of the harbor mouth cause the wave pattern inside the harbor to spread out in semicircles? The answer lies in comparing the size of the harbor mouth to the size of the wavelength of the incoming waves. In the first case, the size of the harbor mouth is considerably larger than the distance between the crests of the waves going through it, and the waves proceed directly through it into the harbor, following a straight line, rectilinear propagation, as waves usually do. In the second case, the size of the harbor mouth is about the same size, or smaller, than the wavelength of the incoming waves, and when this happens, it causes the characteristic pattern, diffraction, that we see in the drawing. Whenever waves pass through an opening that is so small that the wavelength of the waves passing through it seems large in comparison, the waves passing through it diffract. Since light is a wave phenomenon, according to the wave theory of light, it should behave in the same way, and it does. If we place a light source behind a cutout like the one below, it casts a projection on the wall like this one. This is analogous to sea waves entering the large harbor mouth. The width of the cutout is millions of times larger than the wavelength of the light. As a result, the light waves go straight through it, following straight lines and projecting onto the wall a figure with the same shape as the cutout. Notice especially that this projection has distinct borders between the bright area and the dark area. 60 / patterns of organic energy. If we make the cutout no larger than a razor slit so that its Width is roughly as small as the wavelength of the incoming light. The light diffracts now, the sharp boundary between the light area and the dark area disappears, and we see a bright area that fades into darkness at the edges instead of proceeding in a straight line to the wall. The light beam has spread out like a fan. This is diffracted light. Now that you know the punch line, here comes the stove. In 1803, Thomas Young settled once and for all, he thought, the question of the nature of light. He used an experiment that was both simple and dramatic. In front of a light source, Young used sunlight coming through a hole in a screen. He placed a screen with two vertical slits in it. Each slit could be covered over with a piece of material. Sun light /top. View J. Light source. On the other side of the double-slit screen was a wall against which the light coming through the double slits could shine. When the light source was turned on and one of the slits was covered up, the wall was illuminated like the first drawing on the next page. When both slits were uncovered, however, Young made hist of the projection on the wall should have been the sum of the light from the two slits, but it wasn't. Instead, the wall living /61 was illuminated /with alternating bands of light and darkness. The center band was the brightest on both sides. At the center band of light were bands of darkness, then bands of light but less intense than the center band, then bands of darkness etc. as below. How could this happen? The simplicity of the answer is what makes this experiment a great one. The alternating light and dark bands are a well-known phenomenon of wave mechanics called interference. Interference results when the waves of light diffracting from the two slits interfere with each other in some places. These 62 / patterns of organic energy waves overlap and reinforce one another. In other places they cancel each other. In areas where one wave crest overlaps another wave crest, the result is an intensification of light. The light bands, in areas where a crest meets a trough, they cancel each other, and no light reaches the wall. The dark bands. It is just as if we dropped two stones into a pond simultaneously and watched the waves spreading from their points of entry. The waves that the stones make interfere with each other in places where the crests of the waves caused by one stone meet the crests of the waves caused by the other stone. Large waves result in places where the troughs of the waves caused by one stone meet the crests of the waves caused by the other stone. The water is calm. In short, Young's double-slit experiment showed that light must be wave-like because only waves can create interference patterns. The situation, then, was as follows. Einstein, using the photoelectric effect, proved that light is particle-like, and Young, using the phenomenon of interference, proved that light is wave-like, but a wave cannot be a particle and a particle cannot be a wave. That is just the beginning. Since Einstein proved that light is composed of photons, let us go back to Young's double-slit experiment and run it with photons *. This has been done. Suppose that we have a light gun which can fire, in effect, one photon at a tune. The experiment is set up as before, except that only one slit is open. Now we fire the photon, it goes through the open slit, and we mark where it hits the wall using a photographic plate, because we have done this experiment before, \VE. Notice that the photon has landed in an area that would be dark if the second slit were open. That is if the second slit were open, no photons would be recorded in this area. To make sure, we do the experiment again, but this time we leave both of the slits open just as we thought. There are no photons recorded now in the area where the photon hit in. OUI first experiment when both slits are open and interference is present. This area is in the middle of a dark band. The question is, who did the photon in the first experiment know that the second slit was not open? Think about it if we assume a geometrical aspect in the double slit experiment, we will violate the uncertainty relation unless we also assume new locality. Living /63. Both slits are open, there are always alternating hands of illuminated and dark areas. This means that there are always areas where the photons never go, otherwise there would not be any dark areas. If one of the slits is closed, there is no interference and the dark bands disappear. The whole wall becomes illuminated, including those areas which previously were dark when both slits were open. When we fired our photon and it went through the first slit, how did it know that it could go to an area that must be dark if the other slit were open? In other words, how did the photon know that the other slit was closed? The central mystery of quantum theory, wrote Henry Stapp, is how does information get around so quick? How does the particle know that there are two slits? How does the information about what is happening where else get collected to determine what is likely to happen? Here. 3. There is no definitive answer to this question. Some physicists, like E. H. Walker, speculate that photons may be conscious. Consciousness may be associated with all quantum mechanical processes, since everything that occurs is ultimately the result of one or more quantum mechanical events. The universe is inhabited by an almost unlimited number of rather discrete conscious, usually non-thinking entities that are responsible for the detailed working of. Whether Walker is correct or not, it appears that if there really are photons, and the photoelectric effect proves that there are, then it also appears that the photons in the double slit experiment somehow know whether or not both slits are open and that they act accordingly. This brings us back to where we started. Something is organic if it has the ability to process information and to act accordingly. We have little choice but to acknowledge that photons, which are energy, do appear to process information and to act accordingly, and that therefore, strange as it enough, an explanation other than knowing might be sfngeontit jngs a console. Connecting principle 64 / patterns of organic energy. Sound. They seem to be organic since we are also organic. There is a possibility that by studying photons, and other energy quanta, we might learn something about us. The wave-particle duality was the end of the line for classical causality. According to that way of thinking, if we know certain initial conditions, we can predict the future of events. Because we know the laws that govern them in double-slit experiments, we know all that we can know about initial conditions, and we still can't predict correctly what happens to single photons. In experiment 1, for example, only one slit open, we know the origin of the photon, the lamp, its velocity, 186,000 miles per second, and its direction just prior to passing through the open slit. Using Newton's laws of motion, we can predict Where the photon will land on the photographic plate. Let us suppose that we make these calculations. Now let us consider experiment 2, both slits open, again. We know the origin of the photon, its velocity and its direction just prior to passing through the open slit. The initial conditions of the photon in experiment 1 are the same as those of the photon in experiment 2. They both start from the same place, travel at the same speed, go to the same place, and therefore are moving in the same direction just prior to passing through slit number 1. The only difference is that in the second experiment the second slit also is open. Again, using Newton's laws of motion, let us calculate where the photon will land on the photographic plate. Since we used the same figures and the same formulas in both cases, we get identical answers, indicating that the photon in experiment 1 will impact in exactly the same place as the photon in experiment 2. That is the problem. The photon in experiment 2 will not impact in the same area as the photon in experiment 1, because the photon in experiment 1 landed in an area that is a dark band in experiment 2. In other words, the two photons do not go to the same place, even though the initial conditions pertaining to both of them are identical and known to us. We cannot determine the paths of individual photons. We can determine what the wave pattern on the wall will be, but in this case we are interested in a single photon, not waves of them. In other words, we know the pattern that large groups of photons will make, and their distribution in the pattern. Living /65. But we have no way of knowing which photons will go where. All that we can say about a single photon is the probability of finding it in a given plate. The wave-particle duality is one of the thorniest problems in quantum mechanics. Physicists like to have tidy theories which explain everything, and if they are not able to do that, THEV like to have tidy theories about why THEV can't. The wave-particle duality is not a tidy situation. In fact, its untidiness has forced physicists into radical new ways of perceiving physical reality. These new perceptual frames are considerably more compatible with the nature of personal experience than were the old. For most of us, life is seldom black and white. The wave-particle duality marked the end of the either-or way of looking at the world. Physicists no longer could accept the prior position that light is either a particle or a wave, because they had proved to themselves that it was both, depending on how THEV looked at it. Of course, Einstein was aware of the fact that his photon theory contradicted Young's wave theory without disproving it. He speculated that photons were guided by ghost waves. Ghost waves were mathematical entities which had no actual existence. The photons seemed to follow paths which had all the mathematical characteristics of waves, but which in reality did not exist. Some physicists still view the wave-particle paradox this way, but for most physicists, this explanation seems too contrived. It is an answer which appears to make sense, but somehow doesn't explain anything. The wave-particle duality prompted the first real step in understanding the newly unfolding quantum theory in 1924. Bohr and two of his colleagues, H.A. Kramers and John Slater, suggested that the waves in question were probability twins. Probability waves were mathematical entities by which physicists could predict the probability of certain events occurring or not occurring. Their mathematics did not prove correct, but their idea, which was unlike anything that had been proposed before, was sound later, with a different formalism, mathematical structure. The idea of probability waves developed into one of the distinguishing characteristics of quantum mechanics. Probability waves, as Baha'i, Kramers, and Slater thought of them, was an entirely new idea. Probability itself was not new, but this type of probability was. It referred to what 66/patterns of organic energy somehow already was happening, but had not yet been actualized. It referred to a tendency to happen, a tendency that in an undefined way existed of itself, even if it never became an event. Probability waves were mathematical catalogues of these tendencies. This was something quite different from classical probability. If we throw a die in a casino, we know, using classical probability, that the chances of getting the number that we want is 1 in 6. The probability wave of Baha'i, Kramers, and Slater meant much more than that. According to Heisenberg, it meant a tendency for something. It was a quantitative version of the old concept of potentia in Aristotelian philosophy. It introduced something standing in the mid-DLE between the idea of an event and the actual event, a strange kind of physical reality just in the middle between possibility and reality. 5. By 1924, Planck's discovery of the quantum was producing seismic effects in physics. It enabled Einstein to discover the photon, which caused the wave-particle duality, which led to probability waves. The physics of Newton was a thing of the past. Physicists found themselves dealing with energy that somehow processed information, which made it organic, and unaccountably presented itself in patterns, waves. In short, physicists found themselves dealing with woolly patterns of organic energy. Chapter 1. What happens? Quantum mechanics is a procedure. It is a specific way of looking at a specific part of reality. The only people who use it are physicists. The advantage of following the procedure of quantum mechanics is that it allows us to predict the probabilities of certain results provided our experiment is performed in a certain way. The purpose of quantum mechanics is not to predict what actually will happen, but only to predict the probabilities of various possible results. Physicists would like to be able to predict subatomic events more accurately, but at present, quantum mechanics is the only workable theory of subatomic phenomena that they have been able to construct. Probabilities follow deterministic laws in the same way that macroscopic events follow deterministic laws. There is a direct parallel. If we know enough about the initial conditions of an experiment, we can calculate, using rigid laws of development, exactly what the probability is for a certain result to occur. For example, there is no way that we can calculate where a single photon in a double-slit experiment will strike the photographic plate, page 64. However, we can calculate with precision the probability that it will strike it at a certain place, provided that the experiment has been prepared properly and that the results are measured properly. Suppose that we calculate a 60% probability for the photon to land in area A. Does that mean that it can land somewhere else? Yes. In fact, there is a 40% probability that it will. 67. 68 / patterns of organic energy. In that case, asking the question for Jim DeWitt, what determines where the photon will land? The answer given by quantum theory: pure chance. This pure chance aspect was another objection that Einstein had about quantum mechanics. It is one of the reasons that he never accepted it as the fundamental physical theory. Quantum mechanics is very impressive, he wrote in a letter to Max Born, but I am convinced that God does not play dice. 2 generations later, J.S. Bell, a Scottish physicist, proved that he may have been right, but that is another story, which we will come to later. The first step in the procedure of quantum mechanics is to prepare a physical system, the experimental apparatus, according to certain specifications, in an area called the region of preparation. The second step in the procedure of quantum mechanics is to prepare another physical system to measure the results of the experiment. This measuring system is located in an area called the region of measurement, ideally, the region of measurement is far away from the region of preparation, of course. To a subatomic particle, even a small macroscopic distance is a long way. Now let us perform the double-slit experiment using this procedure. First, we set a light source on a table, and then, a short distance away, we place a screen with 2 vertical slits. In it, the area where these apparatuses are located is the region of preparation. Next, we fix an unexposed photographic plate on the opposite side of the screen from the light source. This area is the region of measurement. The third step in the procedure of quantum mechanics is to translate what we know about the apparatus in the region of preparation, the light and the screen, into mathematical terms which represent it, and to do likewise for the apparatus that is located in the region of measurement, the photographic plate. To do this, we need to know the specifications of the apparatus. In practice, this means that we give the technician who sets up the equipment precise instructions. We tell him, for example, the exact distance to place the double-slit screen from the light source, the frequency and intensity of the light that we will use, the dimensions of the 2 slits and their position relative to each other and to the light source, etc. We also give him equally explicit instructions concerning the what happens /69 tiring apparatus, such as where to put it, the type of photographic film that we will use, how to develop it, etc. After we translate these specifications of the experimental arrangement into the mathematical language of quantum theory, we feed these mathematical quantities into an equation that expresses the form of natural causal development. Notice that this last sentence doesn't say anything about what is developing. That is because nobody knows the Copenhagen interpretation of quantum mechanics. Page 37 says that quantum theory is a complete theory because it works, correlates experience, in every possible experimental situation, not because it explains in detail what is going on. Einstein's complaint was that quantum theory doesn't fully explain things, because it deals with group behavior and not with individual events. However, when it comes to predicting group behavior, quantum theory works as advertised in a double-slit experiment. For example, it can predict exactly the probabilities of a Photon being recorded in region O, in region B, in region C, and so forth. Of course, the last step in the procedure of quantum mechanics is actually to do the experiment and get a result. To apply quantum theory, the physical world must be divided into two parts. These parts are the observed system and the observing system. The observed system and the observing system are not the same as the region of preparation and the region of measurement. Region of preparation and region of measurement are terms which describe the physical organization of the experimental apparatus. Observed system and observing system are terms which pertain to the way that physicists analyze the experiment. The observed system, by the way, cannot be observed until it interacts with the observing system. And even then all that we can observe are its effects on a measuring device. The observed system in the double-slit experiment is a photon. It is pictured as traveling between the region of preparation and the region of measurement. The observing system in all quantum mechanical experiments is the environ. According to the complement-IITV argument which is at the heart of the Copenhagen interpretation, the latitude is the choice of possible wave functions. Exactly corresponds to, or at least includes, the latitude in the set of possible experimental arrangements, so that every possible experimental situation or arrangement is covered. Quantum theory 70 patterns of organic energy meant which surrounds the observed system, including the physicists who are studying the experiment while the observed system is traveling undisturbed, propagating in isolation. It develops according to a natural causal law. This law of causal development is called the Schrödinger wave equation. The information that we put into the Schrödinger wave equation is the data about the experimental apparatuses that we have transcribed into the mathematical language of quantum theory. Each set of these experimental specifications that we transcribed into the mathematical language of quantum theory corresponds to what physicists call an observable. Observables are the features of the experiment and nature that are considered to be fixed or determined. When and if the experimental specifications that we have transcribed actually are met, we have transcribed into mathematical language several experimental specifications for the region of measure, meant each one corresponding to a different possible result. The possibility that the photon will land in region O, the possibility that the photon will land in region B, the possibility that the photon will land in region C, etc. In the world of mathematics, the experimental specifications of each of these possible situations in the region of measure meant and in the region of preparation corresponds to an observable. In the world of experience, an observable is the possible occurrence, coming into our experience, of one of these sets of specifications. In other words, what happens to the observed system between the region of preparation and the region of measurement is expressed mathematically as a correlation between two observables, production and detection. Yet we know that the observed system is a particle, a photon. Said another way, the photon is a relationship between two observables. This is a long way from the Bildung concept of elementary particles. For centuries scientists have tried to reduce reality to indivisible entities. Imagine how surprising and frustrating it is for them to come so close. A photon is very elementary, only to discover that elementary particles don't have an existence of their own. Asterisk each set of experimental specifications or bit int can be transcribed into a corresponding pleiadical description _/01 _b corresponds to an observe able in the emethynetical theory. The observe able is f_01 b in the world of our experience. The observable is the possible occurrence, coming into our experience, of the satisfied specifications. What happens /71? As Stapp wrote for the Atomic Energy Commission, an elementary particle is not an independently existing, unanalyzable entity. It is, in essence, a set of relationships that reach outward to other things too. Furthermore, the mathematical picture which physicists have constructed of this set of relationships is very similar to the mathematical picture of a real, physical, moving particle. The motion of such a set of relationships is governed by exactly the same equation which governs the motion of a real moving particle. Wrote Stapp, a long-range correlation between observables has the interesting property that the equation of motion which governs the propagation of this effect is precisely the equation of motion of a freely moving particle. 3. Things are not correlated in nature. In nature things are as they are. Period correlation is a concept which we use to describe connections which we perceive. There is no word correlation. Apart from people there is no concept correlation. Apart from people, this is because all people use words and concepts. Correlation is a concept. Subatomic particles are correlations. If we weren't here to make them, there would not be anvkank points, including the concept of correlation. In short, if we weren't here to make them, there wouldn't be any particles. Asterisk t. The particle is represented 1 / I wave function which has almost all of the